Pluto was once thought to be simple: small, cold, distant, and largely inactive. For decades, it sat at the edge of the solar system as a frozen relic, unchanged since its formation. When the New Horizons spacecraft flew past Pluto in 2015, scientists expected confirmation of that assumption. Instead, they found a world that appeared geologically active, chemically complex, and behaviorally inconsistent with everything we thought we understood about objects that far from the Sun. Since that flyby, Pluto has continued to defy prediction. Its atmosphere is behaving in ways that do not match existing models. Its surface is changing faster than expected. Its internal heat source remains unexplained. And its interaction with space, solar radiation, and its moon, Karen raises questions that planetary science is still struggling to answer. What is happening on Pluto is not fully understood, and in several cases, scientists do not yet agree on what they are even observing. Pluto was supposed to be dead. Before New Horizons, Pluto was categorized as a planetary leftover, a body too small to retain heat, too distant to sustain activity, and too cold to support change on meaningful timescales. Models predicted a world locked in geological stasis for billions of years, its interior frozen solid, its surface shaped only by impacts from passing debris. This assumption was not controversial. It was standard planetary physics applied to a small Kuiper Belt object. Pluto's size reinforced that assumption. With a diameter of roughly 2,300 kilometers, it is smaller than Earth's moon and barely massive enough to hold onto a thin atmosphere during the warmest part of its orbit. Its average surface temperature sits near minus 220 degrees Celsius. At those temperatures, rock behaves rigidly, ice behaves like stone, and chemical reactions slow to near inactivity. There was no obvious mechanism for sustained internal energy. Orbital dynamics also supported the idea of dormancy. Pluto's elongated, tilted orbit takes it far from the Sun for most of its 248 Earth-year cycle. During these long stretches, solar input is minimal. Any residual heat from formation should have dissipated billions of years ago. Without tidal heating from a massive parent planet, like the moons of Jupiter or Saturn, Pluto was assumed to be inert. Even Pluto's atmosphere was expected to be temporary and simple. Scientists predicted that nitrogen ice would sublimate when Pluto approached perihelion, creating a thin atmosphere that would then freeze and collapse back onto the surface as Pluto moved away from the Sun. This cycle was expected to be slow, predictable, and chemically uncomplicated. There was no expectation of long-term atmospheric stability or complexity. That framework shaped mission planning. New Horizons was designed as a reconnaissance mission, not an active monitoring platform. Instruments were optimized for imaging, compositional analysis, and brief atmospheric sampling during a rapid flyby. There was no expectation that Pluto would require ongoing observation to track change. It was meant to be a snapshot of a frozen world. The first images returned by New Horizons began to undermine that entire framework almost immediately. Instead of a crater-scarred ancient surface, Pluto displayed vast smooth plains with almost no impact marks. In planetary science, a lack of craters indicates recent resurfacing. Some regions appeared to be no more than tens of millions of years old, an eye blink on geological timescales. That alone contradicted decades of assumptions. Then came the surface diversity. Mountains made of water ice rose several kilometers high. Broad nitrogen ice plains showed signs of flow, convection, and cellular patterns that implied ongoing movement. Layered terrain suggested repeated deposition and erosion. These were not relic features. They were active processes frozen mid-motion. The atmosphere complicated things further. Instead of collapsing as Pluto receded from the Sun after 2015, the atmosphere persisted. Measurements showed it expanding higher than predicted and containing unexpected hazes and chemical layers. Even more puzzling, later stellar occultation observations suggested the atmosphere might be cooling and contracting in ways that models could not reconcile with known physics. Pluto was not just active. It was active in ways that should not have been possible. The problem was not a lack of data. The problem was that the data contradicted fundamental expectations about small, cold worlds. Every mechanism that could explain what was being observed required assumptions that conflicted with Pluto's size, composition, or thermal history. The more scientists examined the findings, the clearer it became that Pluto was not an outlier. It was a challenge. And that challenge did not stop at the surface. A surface that should not exist. As New Horizons continued transmitting data back to Earth, one feature on Pluto quickly became the center of scientific attention: a vast, bright region shaped like a heart. Officially named Tombol Regio, this area alone overturned many assumptions about what Pluto should look like. One half of the region, a smooth plain called Sputnik Planitia, showed almost no impact craters at all. For a body exposed to billions of years of debris in the outer solar system, this absence was not just unusual, it was statistically improbable. Impact craters are the standard clock of planetary science. The longer a surface has been exposed, the more craters it accumulates. On Pluto, most regions should have been saturated with impacts dating back to the early solar system. Yet Sputnik Planitia appeared young, with crater counts suggesting an age of less than 10 million years, and possibly much younger. That implied active resurfacing on a timescale no one had predicted. The composition of this plain deepened the mystery. Spectral analysis showed that Sputnik Planitia is dominated by nitrogen ice mixed with carbon monoxide and methane ices. At Pluto's temperatures, nitrogen ice behaves very differently from water ice. It can flow, convect, and deform over geological time. What scientists were seeing were large polygonal cells across the surface, each tens of kilometers wide. These cells were not random. Their shapes and boundaries matched models of solid-state convection, where warmer material rises and cooler material sinks. For convection to occur, there must be a heat source. That heat does not need to be intense, but it must be persistent. This was the first major contradiction. Pluto should not have enough internal heat to drive convection in surface ices. Its small size means it should have lost most of its primordial heat long ago. Yet the surface geometry suggested ongoing energy transport from below. Surrounding Sputnik Planitia were towering mountains composed not of rock, but of water ice. On Pluto, water ice is so cold and rigid that it functions like bedrock. Some of these mountains rise more than 3 kilometers high, comparable in height to major terrestrial mountain ranges. Their presence indicated crustal strength and structural support that Pluto was never expected to possess. Equally puzzling was the placement of Sputnik Planitia itself. The basin sits almost exactly opposite Pluto's largest moon, Charon. This alignment is not likely to be coincidence. One leading hypothesis suggests that the basin formed from a massive impact early in Pluto's history, but instead of rebounding and relaxing over time, as expected, the region appears to have gained mass. Nitrogen ice accumulated inside the basin, increasing its weight and causing Pluto to reorient itself so that the basin faced Charon. This process, known as true polar wander, requires Pluto's interior to be mechanically responsive. That again points toward a partially warm or flexible interior, possibly containing a subsurface ocean. Such an ocean would provide a heat reservoir and allow the crust to shift relative to the interior. But the existence of a long-lived ocean inside a body as small and cold as Pluto raises serious theoretical problems. Adding to the confusion, the surrounding terrain shows evidence of repeated cycles of deposition and erosion. Layered plains, sharp boundaries between ice types, and flow-like features suggest that Pluto's surface has been reshaped multiple times. This is not the signature of a world that froze early and remained unchanged. It is the signature of a system still evolving. What made this especially difficult to explain was the lack of an obvious energy driver. Pluto is not tidally heated in the way moons like Europa or Enceladus are. Its orbit with Charon is stable and nearly circular. There is no strong external gravitational flexing. Radioactive decay alone, based on Pluto's estimated composition, should not be sufficient to sustain this level of activity. The surface was not just young, it was organized. Different regions showed distinct geological histories, suggesting that multiple processes were operating simultaneously. Some areas were smooth and convective, others fractured and rigid, and still others heavily cratered and ancient. This patchwork complexity pointed to internal differentiation and long-term evolution. By the time scientists had fully mapped Pluto's surface, it was clear that this was not an isolated anomaly. Pluto was behaving like a scaled-down terrestrial planet, not a frozen Kuiper Belt remnant. The surface alone implied internal processes that planetary formation models could not easily accommodate. And if the surface was this active, it raised a deeper question that scientists could not ignore. What was happening beneath it? Pluto's atmosphere should have collapsed. One of the most unexpected findings from the New Horizons flyby was the behavior of Pluto's atmosphere, which defied nearly every prediction made before the encounter. Pluto was expected to possess only a temporary atmosphere that would freeze and fall back onto the surface as it moved away from the Sun. Instead, measurements showed a complex, layered system that extended far higher than models allowed. Even more troubling, follow-up observations years later suggested the atmosphere was changing in ways scientists could not easily explain. Pluto's atmosphere is primarily composed of nitrogen, with smaller amounts of methane and carbon monoxide. At Pluto's surface temperatures, these gases exist in a delicate balance between solid ice and vapor. This balance was assumed to be tightly controlled by Pluto's distance from the Sun. As Pluto moved farther away after its closest approach in 2015, the atmosphere was expected to thin rapidly. That did not happen. Instead of collapsing, the atmosphere appeared to remain stable, and in some measurements, even expanded. This result contradicted decades of atmospheric modeling for small icy bodies. Data collected during stellar occultations, where Pluto passes in front of distant stars, allowed scientists to probe atmospheric pressure and temperature. These measurements revealed a stratified atmosphere with distinct haze layers extending more than 200 kilometers above the surface. The presence of these layers suggested ongoing chemical reactions driven by sunlight. This was surprising, given the weak solar energy available at Pluto's distance. Ultraviolet radiation appeared sufficient to break apart methane molecules, creating complex hydrocarbons that formed atmospheric hazes. These particles then settled slowly toward the surface, altering Pluto's appearance over time. The persistence of Pluto's atmosphere raised a fundamental question about heat retention. An atmosphere requires energy to remain gaseous, especially in an environment as cold as Pluto's. Scientists examined whether subsurface heat could be leaking upward, slowing atmospheric collapse. Radioactive decay within Pluto's rocky core was considered, but estimates suggested it should be insufficient. Another possibility involved latent heat stored in surface ices, released gradually as Pluto cooled. None of these explanations fully accounted for the observed stability. Seasonal models were also challenged by Pluto's extreme axial tilt and eccentric orbit. These factors create dramatic changes in sunlight distribution over long timescales. Some regions experience decades of continuous darkness, while others receive prolonged illumination. Such conditions complicate predictions of where nitrogen ice should accumulate or sublimate. Atmospheric circulation models struggled to reproduce the observed pressure trends. In several cases, predicted collapse times differed by decades from measurements. This mismatch suggested missing processes or incorrect assumptions. Charon's role in Pluto's atmospheric behavior was also examined. Although Charon lacks an atmosphere of its own, its gravitational interaction influences Pluto's rotation. The two bodies are tidally locked, always showing the same face to each other. This configuration affects how surface ices migrate and how energy is redistributed. Some models propose that Pluto's atmosphere interacts indirectly with Charon through shared orbital dynamics. Evidence remains limited, but the system's complexity makes simple explanations unlikely. The long-term behavior of Pluto's atmosphere remains uncertain. Observations after 2015 indicate cooling trends inconsistent with earlier expectations. If cooling continues, partial collapse may still occur, but the timing is unclear. Future stellar occultations and infrared observations are expected to refine these measurements. However, Pluto's long orbital period means meaningful changes unfold slowly. This makes definitive conclusions difficult within a single human lifetime. What is clear is that Pluto's atmosphere cannot be treated as a simple on-off system. It responds to surface chemistry, internal heat, orbital geometry, and solar radiation simultaneously. This interconnected behavior challenges simplified models developed before direct observation. Pluto appears capable of maintaining atmospheric complexity longer than expected. That capability forces scientists to reconsider how small distant worlds evolve. The implications extend beyond Pluto itself. Other Kuiper Belt objects may possess similar atmospheric behavior that has gone undetected. Without close flybys, transient or persistent atmospheres are difficult to measure. Pluto may represent a class of objects rather than an exception. If so, current models of volatile retention in the outer solar system require revision. These revisions would affect predictions about surface chemistry, climate cycles, and internal structure. They would also influence how scientists interpret data from distant icy worlds. In this sense, Pluto's atmosphere has become a test case for planetary science. The failure of atmospheric predictions highlights a broader issue in planetary modeling. Many models rely heavily on assumptions derived from limited observational data. Pluto demonstrated how those assumptions can break down under direct measurement. This does not invalidate prior work, but it does reveal its limitations. As more distant worlds are observed, similar discrepancies are likely to emerge. Pluto serves as an early warning of that complexity. The mystery of Pluto's atmosphere remains unresolved, but it has reshaped expectations. It demonstrated that distance alone does not dictate inactivity. Small bodies can sustain dynamic processes longer than once believed. This realization has prompted renewed interest in long-term monitoring of Pluto. Future missions, though decades away, may eventually revisit the system. Until then, scientists must rely on indirect methods to track atmospheric evolution. Each new observation refines models while also introducing new questions. Rather than providing closure, Pluto's atmosphere has opened an extended investigation. This investigation continues to influence how scientists interpret planetary behavior at the solar system's edge. The lesson is not that models failed, but that Pluto exceeded expectations. It revealed complexity where simplicity was assumed. That pattern mirrors many recent discoveries in planetary science. As exploration continues, Pluto stands as evidence that the outer solar system remains poorly understood. The atmosphere, once expected to vanish, now anchors an ongoing scientific debate. It is a debate driven by data, not assumption. And that debate underscores how much remains unknown about the smallest worlds shaping planetary theory, far beyond their size or distance from the Sun, and how future discoveries may further disrupt established expectations. Pluto ensures those expectations remain provisional globally. Evidence Pluto may be warm inside. The possibility that Pluto contains internal heat was once considered unlikely, but data from New Horizons forced scientists to reconsider that assumption. Several surface features observed during the flyby are difficult to explain without some form of subsurface warmth. This does not mean Pluto is geologically active in the same way as Earth, but it does suggest that the interior may not be completely frozen, as models once predicted. One of the strongest indicators of internal heat comes from the surface of Sputnik Planitia. The nitrogen ice plains show polygonal cells consistent with slow convection. Convection requires a temperature gradient, with warmer material rising and cooler material sinking. On Pluto, the temperature difference needed is small, but the process still demands a persistent heat source beneath the surface. Without internal warmth, nitrogen ice should behave as a rigid solid, not a slowly circulating layer. The thickness of Sputnik Planitia's ice also matters. Estimates suggest the nitrogen ice layer may be several kilometers deep. For convection to occur throughout such a layer, heat must be supplied from below. Solar energy alone cannot penetrate that deeply, especially at Pluto's distance from the Sun. This leaves internal heat as the only plausible driver. Additional clues come from Pluto's tectonic features. Long fractures, faults, and extensional cracks stretch across large portions of the surface. These structures indicate that Pluto's crust has expanded over time. Expansion suggests that the interior volume increased, which could occur if a subsurface ocean partially froze, causing water to expand as it transitioned to ice. This process would push outward on the crust, creating the observed fractures. The orientation and distribution of these fractures are not random. Many align in patterns consistent with global stress rather than local impacts. That pattern supports the idea of internal restructuring rather than surface damage. The scale of these features also implies that the stresses involved affected the entire crust, not isolated regions. One hypothesis proposes that Pluto once possessed, and may still retain, a subsurface ocean composed of liquid water mixed with antifreeze compounds, such as ammonia. Ammonia lowers the freezing point of water, allowing liquid layers to persist at lower temperatures. If such an ocean exists, it would act as a thermal reservoir, slowly releasing heat over billions of years. Maintaining a subsurface ocean on Pluto presents challenges. Pluto's small size limits the amount of heat generated by radioactive decay. However, if Pluto formed with a higher proportion of radioactive elements than expected, or if heat loss was slower due to insulating layers, an ocean could persist longer than models suggest. This idea remains controversial, but is actively studied. The relationship between Pluto and its moon Charon also factors into internal heat discussions. Pluto and Charon likely formed from a massive collision early in solar system history. Such an impact would have deposited significant energy into both bodies. While much of that heat would dissipate over time, some may have been retained in the interior, especially if insulating ice layers slowed cooling. Sputnik Planitia's position relative to Charon provides another clue. The basin's alignment suggests Pluto reoriented itself after the basin formed. This reorientation is easier to explain if Pluto's interior is at least partially decoupled from its crust, as would be the case with a subsurface ocean. A rigid, fully frozen interior would resist such movement. Thermal models attempting to reproduce Pluto's current state must account for multiple constraints simultaneously. They must explain surface convection, tectonic expansion, atmospheric persistence, and orbital dynamics. No single model fully satisfies all observations. Some models favor a warm interior with a thin ocean layer, while others propose alternative heat transport mechanisms that do not require liquid water. The uncertainty surrounding Pluto's internal temperature highlights a broader issue in planetary science. Many assumptions about small icy bodies are based on indirect observations and simplified models. Pluto demonstrated that these assumptions can fail when confronted with direct data. The planet occupies a transitional category, neither fully inert nor fully active, challenging existing classification schemes. Future observations may provide additional constraints. Measurements of Pluto's gravity field, if obtained during a future mission, could reveal whether a subsurface ocean exists by detecting variations in mass distribution. Long-term monitoring of surface changes may also indicate whether internal processes are ongoing or slowing. At present, scientists cannot definitively state whether Pluto is warm inside. What they can say is that a completely frozen interior is increasingly difficult to reconcile with observed features. The evidence points toward residual heat influencing surface and atmospheric behavior, even if that heat is weak by planetary standards. This possibility carries implications beyond Pluto. If a body this small and distant can retain internal warmth, other Kuiper Belt objects may as well. That would expand the range of environments considered capable of long-term geological or chemical activity. Pluto may not be an exception, but an early example. The question of Pluto's internal heat remains open, but it has already altered scientific expectations. The data forced a shift from certainty to cautious reassessment. Pluto is no longer viewed as a static remnant of formation. Instead, it is treated as a system still responding to its internal and external conditions. That realization continues to shape how scientists approach the outer solar system. Pluto's atmosphere is behaving in unexpected ways. Pluto's atmosphere was once thought to be temporary, fragile, and largely inactive, existing only when the dwarf planet moved close enough to the Sun for surface ices to sublimate. Before the New Horizons mission, many scientists expected the atmosphere to collapse entirely as Pluto receded into the colder parts of its orbit. Instead, observations revealed an atmosphere that is not only present, but dynamically complex in ways that remain difficult to explain. New Horizons detected a thin but structured atmosphere dominated by nitrogen, with trace amounts of methane and carbon monoxide. What surprised researchers was not merely its existence, but its vertical layering and chemical behavior. The atmosphere extends hundreds of kilometers above the surface, far higher than models predicted for a body with Pluto's weak gravity. Maintaining such an extended atmosphere requires more energy than Pluto should reasonably possess. Temperature measurements deepened the mystery. The upper atmosphere was found to be much colder than expected, measuring around -170 degrees Celsius. Prior models predicted a warmer upper layer due to solar heating and methane absorption. Instead, Pluto's atmosphere appears to radiate heat away efficiently, creating a thermal structure that current simulations struggle to reproduce. One of the most puzzling findings was the presence of atmospheric hazes. New Horizons imaged multiple distinct haze layers stacked above Pluto's surface, extending up to 200 kilometers in altitude. These layers suggest active photochemistry driven by sunlight interacting with methane. The resulting complex hydrocarbons clump together, forming particles that slowly settle toward the surface. The haze layers are not static. Their spacing and brightness indicate processes that vary with altitude and time. This implies ongoing atmospheric circulation rather than a passive envelope of gas. For circulation to occur, energy must be transported vertically, yet the source of that energy remains uncertain, given Pluto's distance from the Sun. Pluto's seasonal cycle complicates matters further. Its highly elliptical orbit causes dramatic changes in solar input over time. As Pluto moved away from the Sun after its perihelion in 1989, many expected atmospheric pressure to decrease rapidly. However, stellar occultation measurements taken years after New Horizons show that Pluto's atmospheric pressure has remained stable or even increased slightly. This persistence challenges the idea that Pluto's atmosphere simply freezes out when sunlight diminishes. Instead, it suggests a buffering mechanism, possibly involving subsurface reservoirs of nitrogen ice that release gas slowly over time. Such reservoirs could moderate pressure changes, but their behavior depends on poorly understood thermal properties of Pluto's crust. Pluto's interaction with its moon, Charon, may also influence atmospheric behavior. Charon lacks a substantial atmosphere, yet it shares a binary relationship with Pluto, orbiting a common center of mass. This configuration affects Pluto's rotation and orientation, potentially influencing how sunlight heats different regions over long timescales. Another unresolved issue is atmospheric escape. Pluto's gravity is weak, and early models predicted that atmospheric gases should be escaping into space at significant rates. New Horizons measured escape rates much lower than expected. The atmosphere is leaking, but not nearly as fast as theory predicted. This discrepancy suggests missing physics in escape models, or an unrecognized process limiting gas loss. Methane plays a key role in these dynamics. Though it makes up only a small fraction of the atmosphere, methane strongly absorbs solar radiation and drives chemical reactions. Its distribution is uneven, both vertically and horizontally. Some regions show enhanced methane concentrations, which affects local temperatures and haze formation. The lower atmosphere exhibits temperature inversions that prevent convection near the surface. This means Pluto lacks the kind of weather systems familiar on Earth. Instead, energy transport occurs through slow diffusion and large-scale circulation. How such circulation is maintained with minimal energy input remains an open question. Surface and atmosphere interactions add another layer of complexity. Nitrogen, methane, and carbon monoxide constantly exchange between solid and gaseous phases. This exchange alters surface composition while simultaneously reshaping the atmosphere. The feedback between surface ice distribution and atmospheric pressure creates a coupled system that is sensitive to small changes. Pluto's axial tilt further complicates atmospheric modeling. With an axial tilt exceeding 100 degrees, Pluto experiences extreme seasonal effects, unlike any planet in the inner solar system. Entire hemispheres can remain in darkness or continuous sunlight for decades. This long-term illumination pattern affects where volatiles accumulate and sublimate. Despite detailed observations, scientists lack sufficient long-term data to fully characterize these cycles. New Horizons provided only a snapshot in time. Without continuous monitoring, it is difficult to determine whether current atmospheric conditions are typical or transitional. Comparisons with Triton, Neptune's largest moon, offer partial insights. Triton shares similar composition and exhibits geyser-like plumes driven by seasonal heating. However, Triton's proximity to Neptune introduces tidal effects absent on Pluto. These differences limit direct comparisons, but highlight how small icy bodies can display unexpected atmospheric activity. The persistence and structure of Pluto's atmosphere challenge assumptions about thermal balance, volatile stability, and energy transport in the outer solar system. Existing models must be revised to account for efficient cooling, low escape rates, and sustained circulation under minimal solar input. Pluto's atmosphere is not a fading remnant, but an active system governed by processes that are still not fully understood. Each new measurement raises further questions, rather than resolving existing ones. This uncertainty has shifted Pluto from a solved case to an ongoing investigation. Understanding Pluto's atmospheric behavior has broader implications. If Pluto can maintain such complexity, other distant objects may also possess atmospheres that defy expectations. The outer solar system may host a greater diversity of active environments than previously assumed. Pluto continues to resist simple classification. Its atmosphere behaves neither like a typical planetary atmosphere nor like a transient vapor shell. Instead, it occupies an intermediate regime that forces scientists to rethink how atmospheres function under extreme conditions. The mystery is not that Pluto has an atmosphere, but that it behaves as though it should not. Pluto's surface is actively reshaping itself. For much of the 20th century, Pluto was assumed to be a geologically inert world, frozen solid and unchanged since its formation. Its small size, low internal heat, and extreme distance from the Sun led scientists to believe it lacked the energy required for active surface processes. That assumption was decisively overturned when New Horizons transmitted its first high-resolution images of Pluto's surface. The most striking feature was Sputnik Planitia, a vast, heart-shaped basin composed primarily of nitrogen ice. This region shows clear evidence of ongoing geological activity. Its surface lacks impact craters, indicating it has been resurfaced within the last 10 million years, possibly far more recently. For a body as small as Pluto, such youthfulness was entirely unexpected. Sputnik Planitia is not static. The nitrogen ice within it appears to be in slow motion, convecting like a viscous fluid. Polygonal cells spanning tens of kilometers suggest heat rising from below and cooling at the surface. This convection requires an internal heat source that should not exist according to traditional thermal models for an object of Pluto's size. One possible explanation involves radiogenic heating from radioactive elements within Pluto's rocky core. While weak, this heat may be sufficient when combined with the insulating properties of thick ice layers. Nitrogen ice, unlike water ice, deforms easily at Pluto's temperatures, allowing even small heat inputs to drive large-scale motion. Surrounding Sputnik Planitia are towering water ice mountains, some reaching heights of 5 kilometers. Water ice at Pluto's temperatures behaves like solid rock, meaning these mountains must be structurally supported from below. Their presence indicates crustal strength and tectonic processes that contradict the idea of a simple frozen shell. Cracks and troughs extending hundreds of kilometers across Pluto's surface provide further evidence of tectonic stress. These features suggest that Pluto has expanded over time, likely due to the freezing of a subsurface ocean. When liquid water freezes, it expands, forcing the outer crust to fracture. This process implies that Pluto may have once harbored, or may still harbor, a liquid ocean beneath its icy exterior. Chemical diversity across the surface adds another layer of complexity. Regions rich in methane ice appear bright and reflective, while areas dominated by tholins, complex organic compounds produced by radiation, appear darker and redder. These materials are not evenly distributed, indicating active transport and resurfacing processes. Volatile migration plays a central role in shaping Pluto's surface. Nitrogen, methane, and carbon monoxide ices sublimate and recondense as Pluto's seasons change. Over decades and centuries, these cycles redistribute material across the planet, erasing old features and creating new ones. This seasonal reshaping blurs the line between geological and atmospheric processes. Pluto's extreme axial tilt intensifies these effects. With an axial tilt greater than 90 degrees, entire hemispheres experience prolonged periods of sunlight or darkness lasting decades. During extended sunlight, surface ices sublimate, while prolonged darkness allows them to condense elsewhere. This drives large-scale mass transfer across the surface. The interaction between surface and atmosphere creates feedback loops that amplify change. As nitrogen ice sublimates, atmospheric pressure increases, enhancing heat transport. As pressure rises, more heat can be retained near the surface, accelerating sublimation. These coupled processes can rapidly alter regional landscapes. Impact craters provide additional insight. Many craters appear softened or partially filled, suggesting viscous flow of surrounding ice. Others are nearly erased, implying resurfacing after their formation. The distribution and condition of craters indicate that Pluto's surface is not uniformly active, but varies significantly by region. Charon offers a useful comparison. Pluto's largest moon displays extensive tectonic features, but lacks the volatile-driven resurfacing seen on Pluto. This contrast highlights the importance of nitrogen and methane in enabling geological activity at low temperatures. Without these volatiles, Pluto would likely resemble Charon far more closely. The origin of Sputnik Planitia itself remains debated. One leading hypothesis suggests it formed from a massive impact early in Pluto's history. The resulting basin would have acted as a cold trap, accumulating nitrogen ice over time. The weight of this ice may have caused true polar wander, reorienting Pluto so the basin migrated toward the equator. Such reorientation would further stress the crust, explaining the global network of fractures observed. This scenario links impact history, internal structure, and surface evolution into a single coherent framework, though many uncertainties remain. Pluto's apparent geological vitality forces a reassessment of what constitutes an active world. Traditionally, geological activity was associated with large planets or moons influenced by tidal heating. Pluto demonstrates that even small, isolated bodies can sustain dynamic surfaces under the right conditions. This realization has implications beyond Pluto. Many Kuiper Belt objects share similar compositions and thermal histories. If Pluto can remain active, others may as well. The outer solar system may host a population of worlds far more complex than previously assumed. Despite the wealth of data from New Horizons, many questions remain unanswered. The mission provided only a brief flyby, capturing a moment in Pluto's long history. Without long-term monitoring, it is difficult to determine how rapidly these surface processes operate or how they evolve over time. Future missions could transform understanding. An orbiter would allow continuous observation of seasonal changes, surface motion, and atmospheric interactions. Until then, Pluto's surface remains a case study in unexpected complexity. Pluto's reshaping surface defies the notion of a static, frozen relic. It is a world where ice behaves like rock, mountains rise from volatile plains, and internal processes leave visible marks across vast distances. Each discovery has pushed Pluto further from simplistic models and closer to the category of active planetary bodies. The challenge now is not explaining isolated features, but understanding how all these processes operate together on a world once thought incapable of change. Pluto's internal heat source should not exist. One of the most persistent puzzles raised by Pluto's activity is the question of where its internal energy comes from. Based on its size and age, Pluto should have lost most of its primordial heat billions of years ago. Classical thermal models predict that an object with Pluto's mass should be geologically dead, incapable of sustaining internal motion, tectonics, or convection. Yet surface observations repeatedly point to ongoing internal processes. The most direct evidence comes from Sputnik Planitia. Convective motion in nitrogen ice requires a steady upward heat flux. Even minimal convection demands a temperature gradient that must be maintained over long periods. Without continuous heat input, the nitrogen layer would eventually stagnate. The persistence of this activity suggests Pluto has access to more energy than expected. Radiogenic heating is the most commonly proposed source. Pluto's rocky core likely contains radioactive isotopes such as uranium, thorium, and potassium. As these elements decay, they release heat. While radiogenic heating is well understood in larger bodies, its effectiveness in small objects like Pluto is limited. Calculations suggest it should produce only modest warming, insufficient to drive observed surface dynamics, unless other factors amplify its effects. One such factor may be insulation. Pluto's thick ice shell acts as a thermal blanket, slowing the loss of internal heat. Nitrogen, methane, and water ice layers can trap heat far more efficiently than bare rock. Over billions of years, this insulation could preserve enough warmth to keep subsurface layers from fully freezing. Another possibility involves a subsurface ocean. Multiple lines of evidence suggest Pluto may still harbor a liquid water ocean beneath its ice shell. Tectonic fractures consistent with global expansion point toward freezing water that expanded over time. If freezing is incomplete, residual liquid could remain, acting as both a heat reservoir and a mechanical lubricant. The presence of ammonia compounds could further lower the freezing point of water, allowing liquid to persist at lower temperatures. Ammonia-water mixtures are common in outer solar system bodies and could significantly extend the lifespan of subsurface oceans. This would help explain why Pluto retains internal mobility long after simpler models predict shutdown. Gravitational interactions also play a role. Pluto and Charon form a binary system rather than a traditional planet-moon arrangement. Their mutual gravitational influence creates tidal stresses, though far weaker than those seen in systems like Jupiter and Io. Even minimal tidal flexing, sustained over geological timescales, could contribute small but cumulative amounts of heat. Additionally, the sheer mass of nitrogen ice in Sputnik Planitia may itself influence internal dynamics. The weight of this ice sheet depresses the crust beneath it, potentially altering heat flow patterns. Concentrated loading could channel internal heat upward, focusing activity beneath specific regions rather than distributing it evenly. Thermal models incorporating these effects can reproduce some observed features, but none offer a complete explanation. Small changes in assumptions produce vastly different outcomes, highlighting how sensitive Pluto's internal state is to poorly constrained variables. Core composition, ice thickness, porosity, and conductivity all remain uncertain. What complicates matters further is time. Pluto's current activity must be sustained over millions of years to erase craters and reshape terrain. Short-lived heat bursts are insufficient. Any viable explanation must account for long-term stability rather than transient warming. Comparisons with other Kuiper Belt objects deepen the mystery. Many bodies of similar size appear inactive, heavily cratered, and unchanged. Pluto stands out as an exception rather than the rule. This suggests either Pluto possesses unique internal properties, or that activity among distant icy worlds is more common than current observations reveal. Pluto's relatively large size, compared to most Kuiper Belt objects, may place it just above a critical threshold. Slight differences in mass can produce disproportionate effects on heat retention. Pluto may occupy a narrow regime where internal processes persist while smaller bodies freeze entirely. The implications extend beyond Pluto itself. If small worlds can remain active far longer than expected, models of planetary evolution must be revised. Heat budgets, ice mechanics, and long-term stability assumptions developed for inner solar system planets may not apply in the same way to icy bodies. The inability to directly observe Pluto's interior remains a major limitation. Unlike Earth or Mars, Pluto cannot be studied with seismic instruments or orbiters that monitor gravitational anomalies over time. Researchers must infer internal structure indirectly, relying on surface features and theoretical modeling. Each new model introduces additional uncertainties rather than eliminating them. This does not indicate failure, but rather reflects the complexity of systems operating under extreme conditions. Pluto exists at the edge of planetary science, where established frameworks are pushed beyond their original scope. Future missions could significantly reduce these uncertainties. An orbiter equipped with radar-sounding instruments could probe beneath Pluto's surface, searching for liquid layers. Gravity mapping could refine estimates of core size and density. Long-term monitoring would reveal whether surface activity is steady or episodic. Until such missions occur, Pluto's internal heat source remains unresolved. The evidence clearly shows that energy is present and active, but its origin and sustainability remain contested. This gap between observation and explanation underscores how incomplete understanding of small icy worlds still is. Pluto challenges the assumption that geological activity requires large size or strong tidal forces. It demonstrates that under the right conditions, even distant dwarf planets can remain internally dynamic for billions of years. The question is no longer whether Pluto has internal heat, but how such heat persists against expectations. Solving this problem will reshape theories of planetary longevity across the outer solar system. Pluto's orbit and rotation create extreme long-term instability. Pluto's unusual behavior cannot be understood without examining its orbit and rotation, both of which are extreme even by outer solar system standards. Pluto does not follow a simple circular path around the Sun. Instead, it travels on a highly elliptical orbit that takes it from roughly 30 astronomical units at perihelion to nearly 50 astronomical units at aphelion. This variation dramatically alters the amount of solar energy Pluto receives over time. A single Pluto year lasts approximately 248 Earth years. During that time, Pluto experiences enormous seasonal shifts, unlike those of any major planet. These seasons are not defined by modest temperature changes, but by wholesale redistribution of surface materials and atmospheric mass. Over decades, entire hemispheres transition from deep freeze to sustained sublimation. Pluto's axial tilt further amplifies these effects. With a tilt of about 120 degrees, Pluto is effectively rotating on its side. This causes one pole to face the Sun continuously for decades, while the opposite pole remains in darkness. When Pluto reaches the opposite side of its orbit, the situation reverses. These prolonged illumination cycles drive extreme surface and atmospheric responses. During extended sunlight, nitrogen and methane ices sublimate rapidly, thickening the atmosphere and transporting material across the surface. During prolonged darkness, the same gases condense back onto the ground, thinning the atmosphere. These transitions are slow by human standards, but rapid on geological timescales, reshaping Pluto's surface repeatedly. Pluto's rotation adds another layer of complexity. It is tidally locked with Charon, meaning the same side of Pluto always faces its moon. This locking stabilizes Pluto's spin, but introduces asymmetries in heating and stress distribution. Regions facing Charon experience slightly different gravitational forces than those facing away, potentially influencing tectonic patterns. Orbital resonance with Neptune also plays a role. Pluto completes exactly 2 orbits around the Sun for every 3 orbits completed by Neptune. This resonance prevents close encounters with Neptune but introduces long-term gravitational perturbations. Over millions of years, these interactions subtly alter Pluto's orbital parameters, affecting its climate cycles. The combined effects of orbital eccentricity, axial tilt, and resonance create climate variability far beyond what is seen on Earth or Mars. Pluto does not experience gradual seasonal changes. Instead, it undergoes episodic transitions where volatile materials migrate across vast distances, accumulating in cold traps and disappearing from warmer regions. These processes explain some surface features but raise new questions. Sputnik Planitia, for example, acts as a massive cold trap that collects nitrogen ice during certain orbital phases. Its location near Pluto's equator is unexpected, as cold traps typically form near poles. This suggests Pluto's orientation and orbital history may have shifted over time. True polar wonder offers one possible explanation. The accumulation of dense nitrogen ice in Sputnik Planitia may have altered Pluto's mass distribution, causing the entire dwarf planet to reorient itself. If this occurred, Pluto's rotational axis would shift relative to its surface, redistributing stresses and changing climate patterns. Evidence supporting this hypothesis includes global fracture systems oriented in ways consistent with large-scale reorientation. Such fractures would form as the crust adjusted to new rotational and gravitational conditions. This process links orbital mechanics directly to surface geology. Pluto's orbital instability also affects its atmosphere. When Pluto moves farther from the Sun, atmospheric collapse was expected. Instead, observations indicate delayed response. This lag suggests Pluto's surface and subsurface act as thermal reservoirs, absorbing and releasing heat over long periods rather than responding instantly to solar changes. The delay complicates climate modeling. Traditional models assume near equilibrium conditions, but Pluto operates far from equilibrium. Energy input and output are mismatched in time, producing hysteresis effects where past conditions influence present behavior. This long memory may explain why Pluto's atmosphere remains thicker than expected, even as it recedes from the Sun. Subsurface nitrogen deposits may continue releasing gas long after surface temperatures decline. This mechanism allows Pluto to sustain atmospheric pressure through orbital phases that should otherwise suppress it. The same processes likely influence Pluto's surface evolution. Features formed during one orbital phase may persist into the next, partially erased but not eliminated. Over millions of years, this creates a layered geological record that reflects Pluto's complex orbital history. Comparative planetology highlights Pluto's uniqueness. No other known object combines extreme axial tilt, high orbital eccentricity, binary tidal locking, and volatile-dominated surface chemistry in the same way. Each factor alone would produce unusual behavior. Together they create a system that defies simple classification. The instability is not chaotic in the mathematical sense, but it is unpredictable without precise long-term data. Small variations in orbital parameters can produce disproportionately large environmental changes. This sensitivity makes Pluto difficult to model and easy to misinterpret. Future observations may reveal even more complexity. As Pluto continues moving away from the Sun, scientists expect atmospheric pressure to eventually decline. Whether this happens gradually or abruptly remains unknown. The answer will test competing climate models and refine understanding of volatile transport. Pluto's orbit and rotation are not background details. They are central drivers of its behavior. The dwarf planet's strange activity does not occur despite its orbital characteristics, but because of them. These mechanics force Pluto into cycles of change that challenge assumptions about stability in the outer solar system. Understanding Pluto requires abandoning Earth-centric intuition. Seasons last decades, climate responds slowly, ice flows like rock. Energy is stored, delayed, and redistributed in unfamiliar ways. Pluto is not an anomaly to be dismissed, but a test case for planetary physics under extreme conditions. As long as Pluto remains observable from afar, its evolving state will continue to inform models of distant worlds. Its orbit ensures that no single snapshot captures its full behavior. Pluto must be understood as a system unfolding over centuries, driven by mechanics that operate on scales unfamiliar but fundamental. Pluto's climate cycles operate on timescales humans rarely consider. Pluto's climate cannot be understood using familiar planetary frameworks. On Earth, climate cycles operate over years, decades, or at most thousands of years. On Pluto, meaningful climate change unfolds over centuries and millennia, driven by orbital mechanics, volatile chemistry, and delayed thermal responses. These long cycles complicate interpretation and make short observational windows misleading. Pluto's atmosphere is tightly coupled to surface ices, primarily nitrogen, methane, and carbon monoxide. These volatiles constantly transition between solid and gaseous states, depending on temperature and sunlight. Because Pluto's orbit is highly elliptical, solar energy varies by nearly a factor of 3 between perihelion and aphelion. This variation drives massive redistribution of surface materials over time. When Pluto approaches the Sun, surface nitrogen sublimates rapidly, thickening the atmosphere. Atmospheric pressure rises, allowing heat to be transported more efficiently across the surface. As Pluto moves farther away, temperatures fall and gases condense back onto the ground. This cycle does not occur symmetrically or instantly. Instead, it lags due to subsurface heat storage and the slow movement of volatile ices. Observations from stellar occultations show that Pluto's atmospheric pressure continued to increase even after it passed perihelion in 1989. This defied expectations that pressure would begin dropping immediately. The delay indicates that Pluto's climate system retains energy and releases it gradually, rather than responding directly to changes in solar distance. One explanation involves thermal inertia. Pluto's subsurface layers may absorb heat during periods of high solar input and release it slowly over decades. Nitrogen ice deposits, particularly in Sputnik Planitia, may act as massive thermal buffers. Their depth and composition allow them to store energy long after surface temperatures decline. Pluto's axial tilt magnifies climate extremes. With a tilt exceeding 100 degrees, entire hemispheres remain sunlit or dark for decades. This creates prolonged periods of sublimation in one region, while condensation dominates elsewhere. Over time, this drives global migration of volatiles, reshaping both surface and atmosphere. Unlike Earth, Pluto lacks oceans to moderate temperature swings. Instead, volatile ices perform a similar role, albeit far less efficiently. The result is a climate system that oscillates between extremes without stabilizing influences. These oscillations occur slowly, but with large cumulative effects. Climate models struggle to replicate this behavior. Small changes in assumptions about ice albedo, thermal conductivity, or volatile abundance produce drastically different outcomes. The sensitivity of Pluto's climate highlights how poorly constrained many parameters remain. Another complication is feedback. As nitrogen sublimates and atmospheric pressure rises, increased pressure enhances heat retention near the surface. This can accelerate further sublimation, creating a positive feedback loop. Conversely, condensation reduces pressure, limiting heat transport and accelerating cooling. These feedbacks can amplify relatively small external changes. The spatial distribution of ices also matters. Sputnik Planitia acts as a dominant reservoir, but other regions contribute. Methane-rich areas reflect more sunlight, staying colder and retaining ice longer. Darker regions absorb heat, promoting sublimation. Over time, these differences create uneven climate responses across the surface. Pluto's long climate cycles may also explain the preservation of certain features. Some terrains appear ancient and heavily cratered, while others are smooth and young. These differences suggest that resurfacing occurs episodically rather than uniformly. During certain orbital phases, activity may intensify in specific regions while remaining dormant elsewhere. Comparisons with Triton reinforce this idea. Triton shows active geysers and seasonal plumes linked to its own climate cycles. However, Triton's cycles are shorter due to its closer proximity to the Sun and stronger tidal interactions with Neptune. Pluto operates on longer timescales with weaker external forcing. The lack of continuous monitoring limits understanding. New Horizons observed Pluto during a single season near perihelion. This snapshot captures only one phase of a much longer cycle. Without follow-up missions, it is difficult to determine whether observed conditions represent a peak, a transition, or an intermediate state. Climate models must therefore rely on extrapolation. Scientists simulate thousands of years of Pluto's climate evolution using simplified assumptions. While these models reproduce some observed features, none fully account for atmospheric persistence, resurfacing patterns, and temperature profiles simultaneously. One unresolved issue is whether Pluto's atmosphere ever fully collapses. Some models predict complete freeze-out during aphelion, while others suggest residual gas remains. Current observations favor partial persistence, but the degree remains uncertain. This distinction has major implications for surface chemistry and long-term evolution. If Pluto's atmosphere never fully collapses, even during deep freeze periods, then chemical reactions driven by solar radiation may continue uninterrupted. This would allow haze production and surface modification to persist over longer timescales than previously assumed. Pluto's climate cycles also affect erosion. Sublimation can undercut surface features, while condensation can bury them. Over millions of years, this slow erosion reshapes landscapes without the need for liquid water or strong winds. Ice becomes the primary agent of change. The timescales involved challenge human intuition. A single Pluto season lasts decades. A full climate cycle may span thousands of years. Geological features that appear static may actually be transient on these scales. What looks permanent in images may be part of a slow-moving process. Understanding these cycles matters beyond Pluto. Many Kuiper Belt objects share similar compositions and orbital characteristics. If Pluto's climate operates in this way, other distant bodies may experience comparable cycles. This expands the range of environments considered active in the outer solar system. Pluto demonstrates that climate does not require liquid water or dense atmospheres. Under the right conditions, even trace gases and volatile ices can produce complex, evolving systems. This forces a broader definition of climate applicable to a wider range of worlds. The difficulty lies in verification. Without long-term data, models remain speculative. Pluto's next perihelion will not occur for centuries. Future generations will inherit the task of testing today's predictions. Pluto's climate cycles operate on timescales that exceed political systems, scientific careers, and even civilizations. Yet they are real, measurable, and consequential. Ignoring them leads to misinterpretation. Understanding them requires patience and revised expectations. Pluto is not behaving strangely because it is broken or anomalous. It is behaving according to rules that operate far outside familiar temporal frameworks. Its climate does not rush, stabilize, or resolve. It unfolds slowly, driven by mechanics that reward long observation rather than quick conclusions. Pluto's interaction with space is more complex than expected. Pluto does not exist in isolation. Its behavior is shaped not only by internal and orbital factors, but also by continuous interaction with the surrounding space environment. Before New Horizons, scientists expected these interactions to be minimal due to Pluto's weak gravity and thin atmosphere. Instead, measurements revealed a surprisingly structured and active interaction between Pluto and the solar wind. The solar wind is a stream of charged particles emitted by the Sun that flows throughout the solar system. When it encounters a planet with a strong magnetic field, such as Earth, it is deflected, creating a magnetosphere. Pluto lacks a global magnetic field, leading scientists to predict that the solar wind would strip away its atmosphere efficiently. This expectation was not borne out by observations. New Horizons detected a well-defined boundary where Pluto's atmosphere interacts with the solar wind. This boundary resembles a comet-like interaction rather than a simple erosion process. Atmospheric gases escaping from Pluto become ionized and are carried downstream, forming a long tail that extends millions of kilometers into space. The escape rate, however, was far lower than anticipated. Early models predicted that Pluto could lose its entire atmosphere within a few million years. Instead, measured escape rates were orders of magnitude smaller. This suggests that Pluto's atmosphere is more stable against solar wind erosion than theory predicted. One explanation involves the structure of Pluto's upper atmosphere. The cold temperatures reduce particle velocities, making it harder for gases to escape. Additionally, the presence of methane alters thermal balance and chemistry, influencing how energy is absorbed and radiated. Pluto's interaction with the solar wind also depends on its distance from the Sun. At nearly 40 astronomical units, the solar wind is weaker and more diffuse than near Earth. This reduces the erosive force acting on Pluto's atmosphere, allowing it to persist longer than expected. Another factor is charge exchange. Neutral atmospheric particles can exchange electrons with solar wind ions, creating slow-moving ions that are less effective at stripping atmosphere. This process dissipates energy and reduces atmospheric loss. The absence of a strong magnetic field does not mean Pluto is unprotected. Instead, its atmosphere itself acts as a barrier. As gases escape, they create a region of increased density that slows incoming solar wind particles. This self-shielding effect was underestimated prior to direct measurements. Pluto's space interaction also affects its moons. Charon orbits close enough to pass through Pluto's atmospheric tail. While Charon lacks an atmosphere, its surface may be altered by deposited particles. Over time, this could influence surface chemistry and coloration. The interaction region is dynamic rather than static. Changes in solar wind pressure, solar activity, and Pluto's atmospheric density alter the size and shape of the interaction zone. This variability adds another layer of complexity to Pluto's behavior. The role of dust is less understood. Pluto's atmosphere contains haze particles that may be lofted into space. These particles can interact with charged particles, altering plasma behavior. Dust-plasma interactions are poorly understood even near Earth, making modeling at Pluto particularly challenging. Comparisons with comets are instructive. Like Pluto, comets lack magnetic fields and develop extended interaction regions with the solar wind. However, comets are far more active, releasing large amounts of gas over short timescales. Pluto represents a steady-state version of similar physics operating at much lower intensity. This comparison highlights why Pluto is scientifically valuable. It occupies an intermediate regime between planets and comets, allowing study of processes that bridge these categories. Understanding Pluto's interaction with space improves models of both planetary atmospheres and cometary physics. The interaction also influences atmospheric chemistry. Ionized particles can drive reactions not possible under neutral conditions. These reactions may contribute to the formation of complex hydrocarbons observed in Pluto's haze layers. Over long timescales, space interactions may subtly alter atmospheric composition. Lighter molecules escape more readily, potentially enriching heavier species. This fractionation could influence surface deposits and long-term climate behavior. The balance between atmospheric replenishment and loss is delicate. Sublimation from surface ices resupplies gas, while solar-wind interaction removes it. Pluto's current state suggests these processes are roughly balanced, at least over recent timescales. Whether this balance persists throughout Pluto's orbit remains uncertain. As Pluto moves further from the Sun, atmospheric density decreases, potentially reducing self-shielding. This could increase relative loss rates, leading to periods of enhanced erosion. However, current data suggest that even during low-density phases, complete atmospheric collapse is unlikely. Residual gas likely remains, maintaining some level of interaction with the solar wind at all times. Pluto's interaction with space challenges simplified classifications. It is neither a fully protected planet nor a freely eroding comet. Instead, it occupies a transitional state governed by processes that vary gradually with distance, composition, and solar activity. This complexity underscores the limitations of pre-flyby models. Without direct measurements, key assumptions proved incorrect. Pluto demonstrates that outer solar system environments cannot be accurately understood through extrapolation alone. Future missions equipped with plasma instruments could monitor these interactions over longer periods. An orbiter could observe changes in response to solar cycles, improving understanding of how weak atmospheres survive in hostile environments. Pluto's case has implications beyond the solar system. Many exoplanets orbit at distances where stellar winds are weaker. Some may lack magnetic fields yet retain atmospheres through similar mechanisms. Pluto provides a nearby analogue for studying such worlds. The interaction between Pluto and space is not destructive in a simple sense. It is regulated, structured, and surprisingly stable. This stability contradicts earlier expectations and highlights gaps in understanding of atmospheric escape. Pluto does not passively endure the solar wind. It shapes and modifies the flow around it, creating a complex interface between atmosphere and space. This interface is not an afterthought, but a central component of Pluto's behavior. Understanding Pluto requires integrating internal processes, surface dynamics, climate cycles, and space interactions into a unified framework. Isolating any single factor produces an incomplete picture. The unexpected stability of Pluto's atmosphere illustrates how interconnected these processes are. Pluto's interaction with space is not an anomaly to be explained away. It is evidence that planetary behavior in the outer solar system follows rules that differ from those closer to the Sun. Recognizing and characterizing those rules remains an ongoing challenge for planetary science. Pluto's chemical composition defies simple classification. Pluto's chemical makeup presents a challenge that extends beyond surface observation and atmospheric measurements. While its primary constituents appear straightforward, nitrogen ice, methane ice, water ice, and trace carbon monoxide, their distribution, behavior, and interaction produce outcomes that resist simple explanation. Pluto does not follow the compositional patterns expected of either rocky planets or icy moons. Water ice forms the structural backbone of Pluto's crust. At Pluto's surface temperatures, water ice behaves mechanically like rock rather than ice. This explains why Pluto's mountains, ridges, and tectonic features are composed primarily of water ice rather than nitrogen or methane. These structures indicate a rigid lithosphere capable of supporting significant topography. Nitrogen ice dominates Pluto's volatile inventory. It is highly mobile at Pluto's temperatures and plays a central role in both atmospheric and surface evolution. Nitrogen ice sublimates, flows, and convects in ways more typical of fluids than solids. Its abundance on Pluto is unusual when compared to other Kuiper Belt objects, suggesting Pluto retained more primordial volatiles than most bodies of similar size. Methane ice, though less abundant than nitrogen, has an outsized influence. Methane absorbs solar radiation efficiently, affecting surface temperatures and atmospheric chemistry. Its uneven distribution across Pluto's surface contributes to regional differences in heating, sublimation rates, and haze production. Methane-rich areas tend to be brighter and colder, while methane-depleted regions absorb more heat. Carbon monoxide, present in small amounts, acts as a stabilizing agent. It buffers nitrogen vapor pressure and influences how quickly nitrogen transitions between solid and gas. Though often overlooked due to its low abundance, carbon monoxide plays a key role in regulating Pluto's atmospheric pressure. Pluto's surface also contains complex organic compounds known as tholins. These form when solar ultraviolet radiation and cosmic rays interact with methane and nitrogen in the atmosphere. The resulting molecules settle onto the surface, darkening it and altering its thermal properties. Tholins are responsible for Pluto's reddish coloration and influence surface heating patterns. The presence of tholins introduces feedback mechanisms. Darkened surfaces absorb more sunlight, promoting sublimation of nearby volatiles. This can lead to localized depletion of nitrogen and methane, reshaping surface composition over time. The redistribution of these materials creates chemically distinct regions across Pluto's surface. Pluto's chemical diversity is not static. Volatile migration continuously alters composition. Over decades and centuries, nitrogen and methane shift between hemispheres depending on seasonal illumination. This movement exposes fresh material, buries older deposits, and modifies surface chemistry in ways that complicate age dating. Subsurface chemistry adds further uncertainty. If Pluto harbors a subsurface ocean, interactions between water, ammonia, and dissolved salts could influence surface composition indirectly. Cryovolcanic activity, though not definitively observed, remains a possibility. Such activity would introduce subsurface materials to the surface, altering local chemistry. Spectroscopic data reveal that Pluto's surface is not uniform even at small scales. Adjacent regions can show markedly different absorption features, indicating variations in ice grain size, purity, and mixture. These differences affect how surfaces respond to sunlight and contribute to localized climate effects. Pluto's chemical behavior contrasts sharply with Charon. Charon's surface is dominated by water ice and ammonia compounds, with little volatile nitrogen. This difference highlights Pluto's unique ability to retain light volatiles. The binary system provides a natural experiment, demonstrating how slight differences in mass and formation history produce divergent outcomes. Retention of nitrogen suggests Pluto formed early and accumulated volatiles before the protoplanetary disk dissipated. Its size allowed it to hold onto these materials while smaller objects lost them. This early advantage continues to shape Pluto's present behavior. Radiation processing further complicates composition. Cosmic rays penetrate Pluto's surface, altering molecular structures over time. These processes break apart simple molecules and recombine them into more complex forms. Over millions of years, radiation can significantly change surface chemistry without requiring geological activity. Chemical layering likely exists within Pluto's crust. Repeated cycles of sublimation and condensation may produce stratified deposits with varying compositions. These layers could preserve records of past climate states, though accessing them directly remains impossible with current technology. Pluto's atmosphere reflects surface chemistry, but does not mirror it exactly. Fractionation occurs as lighter molecules escape more readily than heavier ones. Over time, this alters atmospheric composition relative to surface reservoirs. The discrepancy provides clues about long-term atmospheric evolution. The complexity of Pluto's chemistry challenges classification schemes. Pluto does not fit neatly into categories developed for planets, moons, or comets. It shares traits with all three, yet conforms fully to none. This ambiguity complicates comparative studies but enriches understanding. Chemical models must account for interactions across phases. Solid, liquid, and gas phases coexist and interact on Pluto in ways rarely observed elsewhere. Transitions between these phases drive much of Pluto's activity. Laboratory experiments attempt to replicate Pluto conditions, but scaling remains difficult. Ice behavior under Pluto's pressures and temperatures does not translate directly from terrestrial experiments. Uncertainties in physical properties limit model accuracy. Pluto's chemical system is not isolated. External factors such as solar radiation, cosmic rays, and micrometeorite impacts continuously modify surface composition. These inputs add noise to an already complex system. Understanding Pluto's chemistry matters beyond Pluto itself. Many exoplanets orbit at low temperatures, where volatile-dominated surfaces may exist. Pluto serves as a nearby laboratory for studying chemistry under such conditions. The interplay between chemistry and physics on Pluto demonstrates that composition cannot be treated as a passive property. It actively shapes climate, geology, and atmospheric behavior. Ignoring chemical feedback leads to incomplete explanations. Pluto's chemical diversity does not result from a single process, but from the cumulative effect of formation history, retention capability, radiation processing, and ongoing redistribution. Each factor alone is insufficient to explain observed patterns. Despite extensive data, major uncertainties remain. The depth of volatile layers, the extent of subsurface mixing, and the rate of chemical evolution are poorly constrained. Addressing these questions requires long-term observation and possibly in situ exploration. Pluto's chemical composition defies simplification because it operates at the intersection of multiple regimes. It is neither chemically inert nor rapidly evolving. Instead, it occupies a slow but active middle ground. This complexity is not an anomaly, but a natural outcome of Pluto's environment. Its chemistry reflects the conditions under which it formed and the forces that continue to act upon it. Recognizing this allows Pluto to be understood not as an exception, but as a representative of a broader class of distant worlds governed by unfamiliar rules. Pluto's relationship with Charon shapes its evolution. Pluto cannot be understood as a solitary object. Its evolution is deeply intertwined with Charon, the large moon that orbits it. Unlike most planet-moon systems, Pluto and Charon form a binary pair, orbiting a common center of mass that lies outside Pluto itself. This configuration fundamentally alters how both bodies evolve over time. Charon is unusually large relative to Pluto, measuring roughly half Pluto's diameter and about 1/8 its mass. This size ratio is unlike anything seen among the classical planets. The gravitational influence between the two bodies is strong enough to lock them into synchronous rotation, meaning Pluto and Charon always show the same face to each other. This tidal locking occurred early in the system's history. During that process, enormous amounts of rotational energy were dissipated as heat. While most of that energy was lost billions of years ago, its early effects likely influenced Pluto's internal structure, potentially contributing to differentiation between core and mantle. The leading theory for the formation of the Pluto-Charon system involves a massive collision between Pluto and another Kuiper Belt object. The debris from that impact coalesced into Charon and Pluto's smaller moons. Such an impact would have injected significant heat into Pluto, possibly creating or expanding a subsurface ocean early in its history. This early heating may explain why Pluto retained more volatiles than similar-sized objects. A warm interior would slow freezing and allow volatile materials to migrate and stabilize within the crust. While that heat has long since dissipated, its legacy may still influence Pluto's present structure. Charon's gravitational pull continues to affect Pluto today. Although tidal heating is minimal now, the constant gravitational interaction shapes stress patterns in Pluto's crust. Certain fracture orientations observed on Pluto's surface align with expected tidal stress directions, suggesting a long-term imprint of Charon's influence. The binary configuration also affects Pluto's rotation stability. Without Charon, Pluto's axial orientation might vary chaotically over time. Charon acts as a stabilizing presence, limiting extreme rotational shifts. This stability influences Pluto's climate cycles by keeping seasonal patterns predictable over long timescales. Charon's lack of a significant atmosphere provides a useful contrast. Despite forming from the same event and sharing a similar composition initially, Charon lost or never retained volatile nitrogen and methane. This difference highlights how slight variations in gravity and thermal history can produce dramatically different outcomes. Material exchange between Pluto and Charon is subtle but possible. Escaping atmospheric particles from Pluto can reach Charon's surface. Over billions of years, this process may have deposited tholins and other compounds, contributing to Charon's reddish polar regions. Charon's surface shows evidence of its own internal evolution. Vast chasms and tectonic belts suggest global expansion, likely caused by the freezing of a subsurface ocean. This parallels evidence seen on Pluto, indicating both bodies may have shared similar early internal conditions. The synchronization of rotation means Pluto experiences permanent hemispheric asymmetry relative to Charon. Regions facing Charon experience slightly different gravitational conditions than those facing away. Over long timescales, this asymmetry may influence volatile distribution and surface evolution. Pluto's smaller moons add complexity. Styx, Nix, Kerberos and Hydra orbit farther out and exhibit chaotic rotations. Their existence supports the collision-origin hypothesis and provides insight into the debris environment surrounding Pluto after formation. The gravitational interactions within the system influence orbital stability. Pluto and Charon's barycentric motion affects how the smaller moons evolve. This dynamic system provides a natural laboratory for studying orbital mechanics in low-gravity environments. Charon's presence also affects how Pluto interacts with space. As Pluto's atmospheric tail extends downstream, Charon periodically passes through this region. Although Charon lacks an atmosphere, charged particles may interact with its surface, altering surface chemistry subtly over time. The binary nature complicates interpretation of Pluto's evolution. Models developed for isolated dwarf planets may not apply directly. Pluto's development must be understood as part of a coupled system where mass, energy, and angular momentum were redistributed early and continue to exert influence. This relationship challenges classification. Pluto behaves neither like a typical planet nor like a solitary Kuiper belt object. Its binary partnership places it in a distinct category that blurs traditional boundaries. Understanding Pluto without Charon is impossible. Many of Pluto's defining characteristics, including rotational state, internal structure, and surface stress patterns, are inseparable from this relationship. Charon is not an accessory, but a co-architect of Pluto's current state. Future missions could deepen this understanding. An orbiter capable of mapping gravitational fields precisely could reveal how mass is distributed within both bodies. Such data would refine models of their formation and internal evolution. Charon also offers insight into volatile retention thresholds. Comparing Pluto and Charon helps define the minimum conditions required to sustain atmospheres and active surfaces in the outer solar system. The Pluto-Charon system demonstrates that binary formation can produce long-lasting consequences. Early events continue to shape present behavior billions of years later. This challenges assumptions that initial conditions fade into irrelevance over time. Pluto's evolution cannot be reduced to isolated processes. Its internal heat, surface activity, climate cycles, and chemical diversity are all influenced by its partnership with Charon. Ignoring this relationship produces incomplete explanations. Charon's influence is subtle rather than dramatic. It does not dominate Pluto's behavior, but modulates it, guiding evolution rather than dictating it. This subtlety makes its effects harder to identify, but no less important. The binary system also informs broader planetary science. Many exoplanet systems include large moons or binary planets. Studying Pluto and Charon provides a nearby example of how such systems evolve. Pluto's strange behavior is not solely a product of its distance or composition. It is also the outcome of an enduring gravitational relationship established early in its history. That relationship continues to shape its present state in measurable ways. Pluto and Charon represent a paired system whose combined evolution cannot be separated. Understanding one requires understanding the other. Together, they challenge simplified models and highlight the importance of considering relational dynamics in planetary science. The Pluto-Charon system stands as evidence that small bodies can experience complex evolutionary paths shaped by partnership as much as by environment. This realization broadens the scope of how planetary systems are studied and interpreted. Pluto challenges how scientists define planetary activity. For decades, planetary activity was defined using criteria derived almost entirely from the inner solar system. Active worlds were expected to be large, warm, or tidally heated. Small, distant objects were assumed to be inert, shaped only by impacts and radiation. Pluto has forced a reassessment of that framework by demonstrating sustained activity under conditions once thought prohibitive. Before New Horizons, activity was associated with volcanism, tectonics, or erosion driven by liquid water. Pluto exhibits none of these processes in their familiar forms. Instead, it displays activity mediated by solid-state physics, volatile chemistry, and slow thermal exchange. These processes operate quietly but persistently, reshaping the surface over geological timescales. Sputnik Planitia alone invalidated the assumption that small icy bodies are static. Its lack of craters indicates ongoing resurfacing. Nitrogen ice convection functions as a geological engine, even though temperatures are far below those required for liquid water. This demands an expanded definition of what constitutes geological activity. Pluto's tectonic features further complicate classification. Large-scale fractures, graben systems, and extensional faults indicate crustal stress and deformation. These features formed long after Pluto's initial cooling phase, implying internal evolution rather than primordial cracking. Tectonics without plate motion or mantle convection challenges Earth-based models. Atmospheric activity adds another dimension. Although thin, Pluto's atmosphere interacts dynamically with the surface and space environment. Pressure changes, haze formation, and gas escape demonstrate ongoing atmospheric processes. Traditional definitions treat atmospheres as either substantial or negligible. Pluto occupies an intermediate regime that does not fit either category. Climate activity on Pluto also defies expectations. Seasonal cycles involve global redistribution of material, not merely temperature variation. Volatile migration alters surface composition, topography, and albedo. These changes accumulate over time, producing measurable effects without requiring strong energy input. The slow pace of Pluto's processes contributes to misclassification. Activity is often equated with rapid change. On Pluto, change occurs over decades to millennia. Short observation windows underestimate significance. When evaluated over appropriate timescales, Pluto's behavior is clearly dynamic. Comparisons with other bodies illustrate the problem. Mars shows erosion and atmospheric loss, but limited resurfacing today. Europa shows subsurface activity driven by tides. Pluto does not fit either model, yet displays evidence of both internal and surface evolution. It occupies a distinct category that existing labels fail to capture. The difficulty lies partly in language. Terms like active and inactive imply binary states. Pluto demonstrates a spectrum. It is not erupting or flowing in obvious ways, but neither is it frozen in time. Its activity is subtle, cumulative, and persistent. This ambiguity affects classification beyond Pluto. Many Kuiper Belt objects may exhibit similar behavior at levels below current detection limits. If activity is defined narrowly, these worlds remain overlooked. If defined broadly, planetary science must accommodate a wider range of processes. Pluto also challenges assumptions about energy thresholds. Traditional models assume a minimum size or heat flux is required for activity. Pluto operates near or below these thresholds, yet remains dynamic. This suggests that threshold values depend strongly on composition and physical state. Ice mechanics are central to this revision. At Pluto's temperatures, nitrogen ice behaves more like a fluid than a solid. Water ice behaves like rock. This inversion of material behavior undermines intuition developed from Earth conditions. Activity emerges not from heat alone, but from material properties. Pluto's example forces scientists to reconsider the role of volatiles. On Earth, volatiles are secondary to rock-dominated geology. On Pluto, volatiles are primary drivers. This inversion suggests that planetary activity frameworks must be adaptable to different chemical regimes. The concept of habitability is also indirectly affected. While Pluto is not habitable, its ability to sustain complex systems under extreme conditions expands understanding of what planetary systems can do. Activity does not require proximity to a star or large mass alone. Pluto's resistance to simple classification mirrors broader challenges in planetary science. As more worlds are discovered, especially exoplanets, the diversity encountered exceeds traditional categories. Pluto serves as an early warning that classification systems must evolve. The debate over Pluto's status as a planet foreshadowed this issue. Arguments focused on orbital dominance rather than physical behavior. Yet Pluto's physical complexity rivals or exceeds that of some recognized planets. This disconnect highlights limitations in existing definitions. Activity is often associated with potential change. Pluto demonstrates that potential can exist even when change is slow. Its surface is not static, its interior is not inert, and its atmosphere is not ephemeral. Each system operates within narrow margins but remains active. Scientific models struggle because they were not designed for such regimes. Many assumptions break down when applied to Pluto. This does not indicate error in observation, but inadequacy in theory. Pluto's behavior encourages a shift toward process-based classification. Rather than labeling worlds as active or inactive, scientists may need to catalogue dominant processes and their timescales. Pluto would then be recognized for nitrogen-driven resurfacing, volatile climate cycling, and low-level tectonics. This approach aligns better with comparative planetology. It allows meaningful comparison between worlds that differ radically in size, composition, and environment. Pluto becomes a data point rather than an outlier. The challenge is observational. Many processes inferred on Pluto operate too slowly or subtly to detect elsewhere. Without direct exploration, similar worlds may appear inactive simply due to limited resolution or duration of study. Pluto demonstrates the value of direct missions. Without new horizons, its activity would remain speculative or unnoticed. This suggests many assumptions about distant worlds rest on incomplete evidence. The definition of planetary activity is not merely semantic. It influences mission priorities, funding decisions, and scientific focus. Worlds deemed inactive are less likely to be explored. Pluto's example argues for caution in such judgments. Pluto's challenge is not that it behaves unpredictably. It behaves consistently according to physical laws. The unpredictability lies in human expectations shaped by limited experience. As planetary science expands beyond the inner solar system, Pluto's lesson becomes increasingly relevant. Activity manifests differently under different conditions. Recognizing this diversity is essential for accurate interpretation. Pluto does not demand special treatment. It demands better frameworks. Its existence exposes gaps in understanding rather than violating rules. The rules themselves require refinement. Pluto's activity does not announce itself dramatically. It reveals itself through careful measurement, patient analysis, and long-term perspective. This makes it easy to underestimate but impossible to ignore once recognized. The redefinition prompted by Pluto extends beyond one object. It reshapes how scientists interpret small icy worlds across the solar system and beyond. Pluto stands as evidence that planetary activity is not a privilege of size or warmth, but a consequence of physics applied under diverse conditions. Pluto exposes the limits of long-distance observation. For most of its history as a scientific object, Pluto was studied exclusively from afar. Telescopes provided limited data, and models filled the gaps. These models, while mathematically sound, were built on assumptions derived from better-studied planets closer to the Sun. Pluto has revealed how fragile those assumptions can be when applied beyond their original context. Before New Horizons, Pluto appeared as little more than a blurry disk. Variations in brightness hinted at surface diversity, but resolution was insufficient to identify specific features. Atmospheric detection relied on stellar occultations, which provided indirect measurements but no spatial detail. From these sparse datasets, scientists constructed simplified models of a cold, inactive body. Those models predicted a world dominated by ancient craters, a tenuous atmosphere that would collapse as Pluto moved away from the Sun, and minimal geological activity. Each of these predictions was either incomplete or incorrect. The discrepancy highlights the limitations of relying solely on remote sensing, especially for small, distant worlds. Long-distance observation forces scientists to infer processes from incomplete signals. Spectroscopy can identify surface compounds, but it cannot easily reveal their physical state or distribution at fine scales. Light curves indicate rotational variation, but they average over vast areas. These methods obscure localized activity and slow processes. Pluto's case illustrates how averaging masks complexity. Sputnik Planitia, a dominant feature driving much of Pluto's activity, occupies only part of the surface. Its influence on global measurements is diluted when viewed at low resolution. Without close observation, its significance would have been underestimated. Atmospheric behavior presents similar challenges. Stellar occultations provided pressure profiles but no information about haze layers, circulation, or chemical gradients. These details proved essential to understanding Pluto's climate. Remote data suggested simplicity where complexity existed. Thermal measurements suffered comparable limitations. Average surface temperatures obscured extreme local variations. Regions with differing albedo and composition respond differently to sunlight, producing localized thermal effects invisible in global averages. Temporal resolution is another constraint. Observations spanning decades capture only fragments of Pluto's long climate cycles. Conclusions drawn from short timespans risk misinterpreting transient states as stable conditions. Pluto's delayed atmospheric response exemplifies this risk. Distance also limits the ability to detect motion. Ice flow on Pluto occurs slowly, at rates imperceptible over short timescales. Without high-resolution imaging, such motion would go unnoticed. Static images misrepresent dynamic processes as frozen. The interpretation of crater counts demonstrates this issue. Low-resolution images suggested a heavily cratered surface. Higher resolution revealed vast, smooth areas lacking craters. Without close inspection, resurfacing processes remained hidden. Pluto's interaction with the solar wind further exposes observational limits. Plasma boundaries and atmospheric tails are invisible to traditional telescopes. Only in situ instruments could measure these interactions. Prior models lacked key constraints and overestimated atmospheric loss. The gap between prediction and observation is not unique to Pluto. It reflects a broader challenge in planetary science. As exploration extends outward, reliance on indirect methods increases. Pluto serves as a reminder that such methods must be applied cautiously. Extrapolation from inner solar system experience introduces bias. Conditions at Earth, Mars, or Jupiter do not scale linearly to the Kuiper belt. Temperature, pressure, and material behavior differ fundamentally. Assumptions that hold near the Sun may fail at 40 astronomical units. Pluto's discovery of nitrogen ice convection underscores this point. No analogous process exists on Earth. Without precedent, models could not anticipate such behavior. Direct observation was required to reveal it. The limitations extend to compositional analysis. Spectral signatures indicate the presence of compounds, but not their physical context. Grain size, layering, and mixing affect interpretation. Pluto's varied ice textures complicate analysis based solely on spectral data. Even when data exists, interpretation is constrained by model dependence. Scientists must choose among competing explanations, each influenced by assumptions. Without ground truth, uncertainty remains high. Pluto's example argues for the necessity of direct exploration. Flyby missions provide transformative insights even with limited duration. They challenge entrenched assumptions and recalibrate expectations. However, flybys also have limitations. New Horizons observed only one hemisphere in detail. The far side remains largely unexplored. Seasonal variation could not be tracked. Some processes may have been missed entirely. This highlights a paradox. Distant observation is insufficient, but single encounters are incomplete. Comprehensive understanding requires sustained presence, such as orbiters or long-duration missions. Resource constraints make such missions rare. As a result, many distant worlds may remain mischaracterized. Pluto's revelations suggest caution when interpreting data from other Kuiper belt objects observed only remotely. The implications extend to exoplanet science. Most exoplanets are studied through indirect methods. Light curves, spectra, and radial velocities provide limited information. Pluto demonstrates how misleading such data can be without contextual understanding. Pluto's case suggests that exoplanet interpretations may underestimate complexity, especially for small, cold worlds. Features unseen may dominate behavior. Activity may exist below detection thresholds. This does not render remote observation useless. It underscores the need for humility and uncertainty. Models must be treated as provisional rather than definitive. Pluto's transformation from a perceived static body to an active world illustrates the risk of overconfidence. The data was not wrong, but incomplete. Conclusions drawn too early proved fragile. Scientific progress depends on revision. Pluto exemplifies this process. New data forced re-evaluation, not abandonment of theory. Models evolved to accommodate unexpected findings. The challenge is recognizing when models overreach. Pluto's example encourages skepticism toward neat explanations, unsupported by direct evidence. The limits of observation also influence public perception. Pluto's reclassification as a dwarf planet coincided with limited understanding of its complexity. As knowledge expanded, the classification debate took on new dimensions. Understanding Pluto requires acknowledging uncertainty. Not all questions can be answered with current data. Some processes operate beyond observational reach. Pluto reminds scientists that distance matters. The farther an object, the greater the uncertainty. Precision decreases, assumptions increase, and confidence must be tempered. This lesson applies broadly. As exploration pushes outward, reliance on indirect methods will grow. Pluto demonstrates both the power and the limits of such approaches. The solution is not to abandon remote observation, but to integrate it with targeted missions and cautious interpretation. Pluto benefited enormously from a single flyby. Similar investments elsewhere could yield comparable insights. Pluto's exposure of observational limits is not a failure of science. It is a demonstration of its self-correcting nature. Predictions were tested and revised. Understanding improved. Pluto did not behave strangely. It behaved according to rules that were poorly constrained by distant observation. The surprise lay in human expectation, not planetary behavior. Recognizing these limits improves future exploration. Pluto has already reshaped mission planning, encouraging broader consideration of small icy worlds. Pluto stands as a reminder that the universe is more complex than our tools allow us to see at a distance. Only by approaching closer do hidden processes emerge, challenging assumptions and refining understanding. Pluto forces scientists to rethink the outer solar system. Pluto's unexpected complexity has implications that extend far beyond the dwarf planet itself. Its behavior challenges long-standing assumptions about the nature of the outer solar system and the processes that shape it. For decades, this distant region was viewed as a graveyard of frozen remnants, largely unchanged since formation. Pluto has demonstrated that this picture is incomplete. The Kuiper Belt, where Pluto resides, was originally thought to contain small, inert bodies composed mainly of ice and rock. These objects were assumed to lack internal energy and geological evolution. Pluto contradicts this view by showing active resurfacing, climate cycles, and atmospheric persistence under extreme conditions. This realization forces a reassessment of Kuiper Belt objects as a population. Pluto is the largest known member, but it is not unique in composition. Many Kuiper Belt objects contain nitrogen, methane, and water ice. If Pluto can sustain activity, others may as well, albeit at lower levels. The challenge lies in detection. Most Kuiper Belt objects are too small and distant to observe in detail. Their activity, if present, would be subtle and slow. Without close-range exploration, such processes remain hidden. Pluto's example suggests that apparent inactivity may reflect observational limits rather than true dormancy. Pluto's geology also raises questions about internal differentiation. The presence of tectonic features implies a layered interior with a rocky core and icy mantle. This structure suggests early heating sufficient to separate materials. If Pluto differentiated, other large Kuiper Belt objects may have done so as well. The possibility of subsurface oceans extends this reconsideration. If Pluto retained liquid water for extended periods, similar bodies could harbor oceans under the right conditions. This expands the range of environments where liquid water might exist, even far from the Sun. Pluto's climate behavior further complicates the outer solar system narrative. Climate cycles driven by volatile migration demonstrate that distance alone does not preclude dynamic environmental systems. The presence of volatile ices allows climate processes to operate at low temperatures. These findings affect models of solar system evolution. The outer regions may have been more active in the past than previously thought. Heat retention, volatile transport, and surface modification could have occurred across many bodies during early history. Pluto's relationship with Neptune through orbital resonance also highlights the role of gravitational interactions. Kuiper Belt objects are not isolated. Resonances shape their orbits, influence collision rates, and affect long-term stability. These interactions may have contributed to heating and resurfacing in ways not fully appreciated. The realization that Pluto is active alters how scientists interpret crater counts in the Kuiper Belt. Crater density is often used to estimate surface age. If resurfacing occurs more frequently than assumed, age estimates may be overstated. This affects timelines for solar system evolution. Pluto's volatile inventory also informs formation theories. Retaining nitrogen and methane requires early formation and sufficient mass. Pluto's existence suggests that the early solar system produced a wider range of large icy bodies than currently observed. Many of these bodies may have been lost or altered through collisions and migration. Pluto may represent a survivor rather than an exception. Its preservation allows a glimpse into conditions that were once more common. Pluto's complexity also influences classification debates. The distinction between planets and smaller bodies becomes less meaningful when physical behavior overlaps. Activity, differentiation, and climate processes are not exclusive to large planets. This does not mean classification is irrelevant, but it suggests that physical properties deserve greater emphasis. Pluto's behavior aligns more closely with planets than with inert debris. The impact extends to mission planning. Pluto's flyby demonstrated the scientific value of exploring distant icy worlds. It strengthened arguments for missions to other Kuiper Belt objects and dwarf planets. Future missions may reveal whether Pluto is representative or exceptional. Targets such as Eris, Makemake, and Haumea could display their own forms of activity. Each discovery would refine understanding of outer solar system diversity. Pluto's influence reaches exoplanet science as well. Many exoplanets orbit at distances where volatile-dominated surfaces are likely. Pluto provides a nearby example of how such worlds behave. Exoplanet models often rely on assumptions derived from inner solar system planets. Pluto shows that these assumptions may not hold universally. Worlds dominated by ices and low-energy processes may behave very differently. Pluto also informs habitability discussions. While it is not habitable, its ability to sustain complexity under extreme conditions suggests that life-supporting environments may exist in unexpected places. The outer solar system may host a spectrum of environments that challenge simple temperature-based criteria. Internal heat, chemical composition, and orbital dynamics all play roles. Pluto's example emphasizes the importance of composition. Nitrogen ice, rare closer to the Sun, dominates Pluto's activity. This highlights how chemical diversity shapes planetary behavior. Understanding the outer solar system requires integrating physics, chemistry, and dynamics. Pluto demonstrates that isolating factors leads to incomplete explanations. The shift in perspective prompted by Pluto mirrors earlier paradigm changes. Just as Jupiter's moons revealed tidal heating, Pluto reveals volatile-driven geology. These shifts often face resistance. Established models are deeply embedded. Pluto's data forced revision rather than incremental adjustment. The process underscores the value of exploration. Without new horizons, Pluto would remain mischaracterized. Data transforms speculation into evidence. Pluto's lesson is caution. The outer solar system should not be dismissed as static or simple. Complexity can arise under conditions far removed from terrestrial experience. As exploration continues, Pluto will serve as a reference point. It sets expectations for what small, icy worlds can do. The outer solar system is not merely a boundary region. It is an active component of planetary science that informs formation, evolution, and diversity. Pluto's behavior suggests that the solar system's architecture is more dynamic than previously thought. Activity does not stop at the frost line. The challenge now is extending this understanding beyond Pluto. Observations must be combined with modeling and future missions. Pluto has already reshaped scientific priorities. It demonstrated that distant worlds deserve attention not despite their remoteness, but because of it. The outer solar system is not a relic. It is a region where processes continue to unfold slowly but meaningfully. Pluto forces scientists to rethink not only one object, but an entire region of the solar system. Its influence on theory, observation, and exploration will persist long after the flyby data has been fully analyzed. Pluto stands as evidence that assumptions about inactivity at great distances are flawed. The outer solar system is not quiet. It simply operates on timescales and mechanisms that require patience to understand. Pluto alters how scientists think about habitability. Pluto is not a candidate for life as we understand it, yet its behavior has quietly reshaped how scientists think about habitability in the solar system. Traditionally, habitability has been tied closely to distance from a star and the presence of liquid water on a planet's surface. Pluto challenges this narrow framing by demonstrating that complex, long-lived systems can exist far outside conventional habitable zones. Habitability discussions often focus on energy availability. Worlds near their stars receive sufficient heat to maintain liquid water, while distant objects are assumed to be frozen and inactive. Pluto contradicts this assumption by sustaining internal and surface processes with minimal solar input. Its activity is driven not by warmth, but by chemistry, insulation, and delayed thermal response. The possibility of a subsurface ocean beneath Pluto's icy crust is central to this reconsideration. While Pluto's surface is inhospitable, a liquid layer beneath kilometers of ice could remain stable for extended periods. Such an environment would be shielded from radiation and temperature extremes, conditions that are considered favorable for certain forms of life. Subsurface oceans are no longer viewed as rare exceptions. Moons such as Europa, Enceladus, and Titan have already expanded this category. Pluto adds a new dimension by suggesting that even isolated dwarf planets may retain liquid water without strong tidal heating. The energy sustaining such an ocean on Pluto would be modest but persistent. Radiogenic heating, combined with insulation from thick ice layers, could slow freezing for billions of years. The presence of ammonia compounds would further lower freezing temperatures, increasing the likelihood of long-term liquid reservoirs. Habitability does not require active volcanism or plate tectonics. It requires stability, chemical diversity, and energy gradients. Pluto appears capable of providing at least some of these conditions internally, even if its surface remains hostile. Pluto's chemistry also informs habitability discussions. Complex organic molecules form naturally in its atmosphere and settle onto the surface. These tholins demonstrate that prebiotic chemistry can occur in cold, distant environments. While these compounds are not evidence of life, they show that essential chemical building blocks can form far from stars. The transport of these materials into a subsurface ocean, if one exists, is uncertain. However, fractures and tectonic features could provide pathways over geological timescales. Even limited exchange could introduce organics into protected environments. Pluto's long-term stability matters. Habitability requires time. Worlds that experience rapid catastrophic change are less likely to support sustained biological processes. Pluto's slow evolution, operating over millions of years, offers a degree of stability unusual for small bodies. Climate cycles on Pluto, though extreme, are predictable. Seasonal redistribution of volatiles follows orbital mechanics rather than chaotic variation. This predictability could support stable internal conditions, even as surface environments change. The broader implication is that habitability should not be defined solely by surface conditions. Subsurface environments may be equally important, especially in the outer solar system. Pluto strengthens the case for expanding habitability criteria beyond traditional limits. This shift affects how scientists evaluate other distant objects. Kuiper belt objects, once dismissed as irrelevant to life, may host subsurface environments worth consideration. Even if life never arises, studying these environments improves understanding of chemical evolution. Pluto also highlights the importance of energy efficiency. Life does not necessarily require abundant energy. On Earth, some organisms thrive in extreme environments with minimal resources. Pluto's internal gradients, though weak, could support similar processes in theory. The presence of long-lived oceans also influences planetary evolution. Liquid layers enable chemical reactions and material transport that solid ice cannot. This internal dynamism contributes to geological and chemical complexity. Pluto's example challenges the assumption that small size precludes habitability. Mass matters, but composition and structure matter as well. Pluto retained volatiles and heat long enough to support complex internal systems. The distinction between habitable and uninhabitable worlds becomes less binary. Pluto occupies a gray area where certain conditions align while others do not. Recognizing this spectrum enriches planetary science. Pluto also affects how exoplanets are evaluated. Many exoplanets orbit far from their stars. If Pluto-like processes operate elsewhere, habitable environments may exist in unexpected locations. Models of exoplanet habitability often rely on simplified criteria. Pluto demonstrates the need for nuanced approaches that consider internal structure, chemistry, and thermal history. The challenge is observational. Subsurface oceans are difficult to detect even within the solar system. Extrapolating to distant systems requires caution. Pluto provides a nearby test case for refining detection strategies. Future missions to Pluto could clarify these issues. Instruments capable of probing beneath the surface could confirm or refute the presence of liquid layers. Such data would directly inform habitability models. Pluto's contribution is conceptual rather than practical. It expands the range of environments considered worthy of study. This expansion does not imply that life is common, but that the conditions supporting complexity are more diverse than previously thought. Habitability is often framed in terms of human relevance. Pluto forces a shift toward a more universal perspective. Life, if it arises, adapts to available conditions rather than ideal ones. Pluto also underscores the importance of timescale. Processes that appear negligible over years become significant over millions of years. Habitability assessments must account for long durations. The presence of an atmosphere, even a thin one, influences habitability indirectly. Atmospheric chemistry produces organics and regulates surface interactions. Pluto's atmosphere demonstrates that even minimal atmospheres can be chemically active. The retention of an atmosphere over long timescales further supports internal stability. Complete atmospheric loss would isolate the surface chemically. Pluto's persistence suggests balance. Pluto's internal evolution may have passed through more favorable conditions in the past. Early warmth and higher atmospheric pressure could have enhanced internal exchange. Habitability potential may vary over time. This temporal dimension complicates classification. A world may be habitable during one epoch and inhospitable during another. Pluto's history may include such transitions. Pluto's role is not to redefine habitability as universal, but to complicate it. It resists simple exclusion from discussion. The study of Pluto encourages interdisciplinary approaches. Geophysics, chemistry, climatology, and astrobiology intersect in unexpected ways. This integration enriches understanding. Pluto demonstrates that habitability research should not focus exclusively on Earth analogues. Alternative pathways may exist under radically different conditions. This realization broadens scientific curiosity. Worlds once considered irrelevant become meaningful data points. Pluto's influence extends beyond its physical properties. It reshapes how scientists frame questions and define boundaries. The outer solar system emerges not as a sterile region, but as a diverse set of environments with varying potential. Pluto does not suggest life exists everywhere. It suggests that the universe offers more ways for complexity to arise than once assumed. Recognizing this diversity strengthens planetary science. It encourages exploration guided by evidence rather than assumption. Pluto alters habitability discussions not by offering answers, but by revealing overlooked possibilities. Its contribution lies in expanding the conceptual landscape within which life is considered. Pluto reveals how little is known about distant worlds. Pluto's exploration has made one fact unmistakably clear. Scientific understanding of distant worlds remains incomplete. Prior to direct observation, Pluto was treated as a solved problem, a cold remnant whose behavior could be inferred from basic physical principles. The New Horizons mission demonstrated that such confidence was misplaced, revealing layers of complexity that existing models did not anticipate. The assumption that small, distant bodies are geologically inert proved incorrect. Pluto's surface shows evidence of ongoing resurfacing, tectonic deformation, and volatile-driven processes. These findings were not predicted by prevailing theories, indicating gaps in how planetary evolution is understood beyond the inner solar system. One major limitation lies in scaling laws. Many models assume that processes observed on large planets can be scaled down proportionally for smaller bodies. Pluto contradicts this assumption. Its activity is not a reduced version of Earth or Mars geology, but a distinct regime governed by different materials and conditions. Ice-dominated physics operates differently from rock-dominated physics. At Pluto's temperatures, nitrogen ice flows while water ice remains rigid. This inversion of expected behavior undermines intuition developed from terrestrial experience. Models that fail to account for these material properties yield inaccurate predictions. Another gap involves thermal evolution. Pluto retains heat far longer than expected. Traditional models predicted rapid cooling and internal shutdown. Instead, evidence suggests persistent internal gradients capable of driving surface change. This indicates that heat retention mechanisms in icy bodies are poorly constrained. The uncertainty extends to atmospheric dynamics. Pluto's atmosphere defies simple categorization. It is neither transient nor stable in conventional terms. Its persistence, structure, and interaction with space challenge existing escape models and climate simulations. The mismatch between predicted and observed atmospheric loss rates highlights limitations in understanding how weak atmospheres interact with solar wind at large distances. Pluto demonstrates that even thin atmospheres can self-regulate in ways not previously recognized. Observational bias plays a role. Prior to New Horizons, data resolution was insufficient to detect localized activity. Global averages masked regional processes. This suggests that other distant objects may harbor similar activity undetected due to observational constraints. Pluto's case underscores the danger of over-reliance on indirect data. Spectral signatures, light curves, and occultations provide valuable information but cannot capture full complexity. Direct exploration remains essential for validating models. The challenge is compounded by timescale mismatch. Pluto's processes operate slowly, unfolding over decades or longer. Short observation windows risk misinterpreting long-term trends as anomalies or noise. This temporal limitation affects climate interpretation. Pluto's delayed atmospheric response illustrates how present conditions reflect past states. Without long-term monitoring, cause and effect are difficult to disentangle. Pluto also exposes uncertainty in formation theories. Its volatile richness suggests early formation and retention, but precise timelines remain debated. The diversity among Kuiper Belt objects indicates multiple formation pathways. Collisional history adds complexity. Early impacts may have reshaped Pluto's interior and surface. The extent and consequences of these events remain uncertain, affecting interpretation of present features. Comparative planetology is challenged by limited sample size. Pluto is one data point among many poorly characterized objects. Drawing general conclusions from a single example is risky, yet unavoidable given current data. This uncertainty does not undermine Pluto's significance. Instead, it highlights the need for cautious generalization and continued exploration. Pluto serves as a reminder that planetary science is an evolving discipline. The implications extend to exoplanet research. Most exoplanets are studied remotely under conditions even more challenging than Pluto. If Pluto can surprise, distant exoplanets likely harbor unanticipated behavior. Models of exoplanet atmospheres, interiors, and climates often rely on simplified assumptions. Pluto suggests that such models may underestimate complexity, especially for cold, volatile-rich worlds. The discovery of unexpected processes forces revision rather than abandonment of theory. Pluto's data refine existing frameworks, identifying where assumptions fail and where new physics must be incorporated. The challenge lies in identifying which aspects of Pluto are unique and which are representative. Without exploring additional Kuiper Belt objects, this distinction remains unclear. Future missions could address this gap. Flybys of other dwarf planets would reveal whether Pluto's activity is common or exceptional. Orbiters would provide long-term data critical for understanding slow processes. The limitations revealed by Pluto also affect prioritization. Worlds previously considered uninteresting may warrant closer inspection. Scientific value cannot be judged solely by size or proximity. Pluto demonstrates that diversity increases with distance. The outer solar system hosts environments unlike those closer to the Sun. Understanding this diversity requires tailored approaches rather than uniform models. The difficulty of studying distant worlds is not merely technological, it is conceptual. Scientists must be willing to revise assumptions and accept uncertainty. Pluto's example encourages humility. Predictions based on limited data are provisional. Confidence must be proportional to evidence. This humility strengthens science. Pluto's surprises did not invalidate theory, but improved it. Models are now more robust because they account for unexpected behavior. The process also highlights the importance of interdisciplinary work. Understanding Pluto requires integrating geophysics, atmospheric science, chemistry, and orbital dynamics. No single field suffices. The gap between expectation and observation on Pluto reflects broader challenges in planetary science. The universe does not conform to simplified categories. Pluto's lesson is not that science failed, but that exploration matters. Without data, even well-reasoned models remain speculative. As exploration advances, similar revisions are inevitable. Each new world studied closely will challenge assumptions in unforeseen ways. Pluto represents a transition point. It marks the shift from treating distant worlds as predictable to recognizing them as complex systems. This recognition influences how questions are framed. Instead of asking whether a world is active, scientists ask how activity manifests under specific conditions. Pluto's contribution lies in expanding the scope of inquiry. It reveals that distant worlds cannot be understood by analogy alone. The outer solar system emerges as a region of active research rather than a repository of leftovers. Pluto stands at the center of this shift. The uncertainty Pluto exposes is not a weakness. It is an opportunity to refine understanding and expand exploration. Pluto reveals how much remains unknown. It invites continued investigation rather than closure. The dwarf planet's behavior demonstrates that scientific knowledge advances through confrontation with the unexpected. Pluto does not provide definitive answers. It provides better questions. By revealing the limits of current understanding, Pluto advances planetary science more effectively than confirmation ever could. The lesson is clear. Distant worlds are not simple. They demand careful study, long-term observation, and openness to revision. Pluto shows that exploration is essential for understanding complexity beyond familiar boundaries. Its revelations mark the beginning rather than the end of inquiry into the outer solar system. Pluto stands as a reminder that the farther science reaches, the more it must be prepared to encounter the unknown. Pluto suggests that time matters more than distance. Pluto has demonstrated that distance from the Sun is not the sole determinant of planetary behavior. Instead, time plays an equally critical role. Processes unfolding over millions or billions of years can sustain activity long after initial energy sources fade. Pluto's evolution shows that slow change, when given enough time, can rival faster processes operating closer to the Sun. The outer solar system operates on extended timelines. Orbital periods span centuries, seasonal cycles last decades, and climate responses lag behind changes in solar input. Pluto's behavior cannot be interpreted correctly without accounting for these long durations. Short-term observation obscures patterns that only become visible across geological timescales. Pluto's internal heat illustrates this principle. While its heat output is minimal by planetary standards, it has persisted long enough to influence surface and internal processes. Radiogenic decay releases energy slowly but continuously. Over billions of years, even weak heating accumulates into meaningful effects. This cumulative nature explains how Pluto can sustain activity despite its small size. Traditional models often emphasize instantaneous energy flux. Pluto demonstrates that sustained low-level input can be equally important when time is considered. Surface evolution reflects this slow accumulation. Nitrogen ice convection does not reshape terrain quickly, but over millions of years it erases craters and modifies landscapes. What appears static in human timescales is dynamic when viewed through geological perspective. Atmospheric persistence also depends on time. Pluto's atmosphere does not respond immediately to orbital changes. Instead, it integrates past conditions, releasing stored volatiles long after surface temperatures decline. This delayed response creates stability that models focusing on short timescales fail to capture. Pluto's climate cycles illustrate temporal integration. Each orbital phase leaves residual effects that influence subsequent states. Volatile deposits migrate gradually, and their redistribution carries memory of prior illumination patterns. This temporal memory complicates interpretation. Observations reflect not only current conditions, but accumulated history. Without understanding that history, present behavior appears anomalous. Pluto's geological features similarly encode time. Fractures, basins, and resurfaced plains represent integrated responses to slow internal and external forces. Their existence implies long-term processes rather than brief events. The concept of activity must therefore incorporate duration. A world need not exhibit dramatic change to be active. Persistent slow change can be equally transformative given sufficient time. This insight challenges the assumption that distant worlds are irrelevant due to low energy environments. Pluto shows that time compensates for low energy, enabling complexity to emerge gradually. The implication extends beyond Pluto. Many Kuiper Belt objects experience similar conditions. Over billions of years, even weak processes may shape their evolution in significant ways. Distance affects rate, not inevitability. Processes proceed slowly far from the Sun, but they still proceed. Pluto exemplifies this distinction. Time also influences detectability. Slow processes are harder to observe directly. Short missions may miss gradual change. Pluto's example cautions against dismissing inactivity based on brief observations. Pluto's internal structure likely evolved slowly. Differentiation, ocean formation, and freezing occurred over extended periods. These processes leave lasting imprints detectable today. The freezing of a subsurface ocean would not occur uniformly. Gradual solidification could drive tectonic stress over millions of years, explaining Pluto's fracture systems. Similarly, volatile loss is not instantaneous. Atmospheric escape occurs steadily but slowly. Over billions of years, composition may change significantly, even if annual loss rates appear negligible. This perspective reframes planetary evolution. Instead of asking whether energy is sufficient now, scientists must consider whether it has been sufficient over long durations. Pluto's early history likely included higher energy conditions. Residual heat from formation and impacts would have been greater. The slow dissipation of that energy influences present behavior. Understanding Pluto therefore requires reconstructing its timeline rather than focusing solely on its current state. Each stage builds upon the previous one. This temporal approach complicates modeling. Long-term simulations are computationally challenging and sensitive to initial conditions. Small uncertainties compound over time. Despite these challenges, incorporating time improves explanatory power. Pluto's delayed atmospheric response, resurfacing patterns, and tectonic features align more closely with models emphasizing long-duration processes. The importance of time also affects comparison with other bodies. Worlds of similar size may differ significantly if their thermal histories diverged early. Pluto's retention of volatiles suggests it cooled more slowly or formed earlier than some neighbors. Time of formation influences present behavior. The concept applies to habitability as well. Potentially habitable environments may exist intermittently rather than continuously. Pluto's history may include periods more favorable than today. Time-dependent habitability challenges static definitions. a world may transition through habitable phases without sustaining them indefinitely. Pluto's case encourages viewing planetary evolution as a continuum rather than a snapshot. Present conditions are one frame in a long sequence. This perspective aligns with Earth's history. Earth's habitability has varied dramatically over time. Pluto shows that even distant worlds experience evolutionary trajectories. Recognizing the role of time broadens scientific inquiry. It encourages investigation of processes previously dismissed due to low current activity. Pluto also highlights the importance of patience in science. Conclusions drawn from limited data risk overlooking slow processes. Future missions designed for long-duration observation would address this gap. Orbiters could track changes over years or decades, revealing dynamics invisible in flybys. Until then, Pluto serves as a reminder that planetary behavior cannot be fully understood without considering time. Distance sets the stage, but time writes the script. Pluto's story unfolds slowly, but its cumulative effects are unmistakable. The dwarf planet teaches that energy thresholds are not absolute. Time allows marginal processes to become consequential. This lesson applies broadly. From icy moons to distant exoplanets, time may enable complexity under conditions that appear unfavorable at first glance. Pluto suggests that planetary science must adopt longer horizons. Short-term observations capture only fragments of reality. The recognition of time's importance reshapes interpretation. Pluto's behavior becomes coherent when viewed as the product of prolonged interaction between energy, material properties, and orbital dynamics. This coherence emerges only when time is treated as a central variable rather than a background parameter. Pluto's evolution is not anomalous. It is an example of slow planetary change operating within physical constraints. By emphasizing time, Pluto bridges the gap between low-energy environments and observable activity. This perspective transforms Pluto from a puzzling exception into a predictable outcome of long-term processes. The dwarf planet demonstrates that distance limits rate, not possibility. Time allows Pluto to remain dynamic long after simpler models predicted inactivity. This realization refines understanding of planetary systems as evolving entities shaped by persistent forces. Pluto's lesson is not that everything changes quickly, but that enough time guarantees change. Recognizing this helps scientists interpret distant worlds more accurately. Pluto stands as evidence that planetary behavior is governed by the interplay of energy and time. Ignoring either leads to incomplete understanding. Pluto suggests that future discoveries will continue to challenge assumptions built on short timescales. The outer solar system is not frozen in stasis. It is evolving slowly, shaped by processes that reward patience. Pluto embodies this principle. Its story unfolds over epochs rather than moments. Understanding Pluto means learning to think in planetary time. This shift in perspective is essential for interpreting the universe beyond familiar boundaries. Pluto's atmosphere is acting out of sequence. Pluto's atmosphere continues to behave in ways that conflict with established expectations. Based on its increasing distance from the Sun since perihelion in 1989, scientists expected the atmosphere to steadily collapse as surface temperatures declined. Instead, measurements taken years after the New Horizons flyby suggest that atmospheric pressure remained higher than predicted, indicating a delayed or altered response. Pluto's atmosphere is composed primarily of nitrogen, with smaller amounts of methane and carbon monoxide. These gases are in constant exchange with surface ice reservoirs. As temperatures rise, surface ices sublimate and thicken the atmosphere. As temperatures fall, gases freeze back onto the surface. This process is known as volatile cycling and is central to Pluto's climate. The unexpected persistence of Pluto's atmosphere implies that volatile cycling is not synchronized directly with instantaneous solar input. Instead, it appears to be governed by stored thermal energy and subsurface heat transfer that operates over extended timescales. This introduces a lag between orbital position and atmospheric response. Occultation observations from Earth-based telescopes provide key evidence. By measuring how Pluto's atmosphere bends starlight during stellar occultations, astronomers can estimate atmospheric pressure and density. Data collected in the years following 2015 showed pressure levels that were not declining as quickly as models predicted. This discrepancy forced scientists to revise assumptions about Pluto's thermal inertia. Thermal inertia describes how resistant a material is to temperature change. Pluto's surface appears to store heat more efficiently than previously believed, slowing the freezing of atmospheric gases. Nitrogen ice plays a critical role. Its phase transitions occur at relatively narrow temperature ranges. Once sublimation begins, it can persist until significant cooling occurs. This creates hysteresis, where the state of the atmosphere depends not only on current temperature, but also on prior conditions. Pluto's Sputnik Planitia basin amplifies this effect. Its vast nitrogen ice reservoir acts as a climate regulator. During warmer periods, it releases gas into the atmosphere. During cooling phases, it absorbs gas slowly rather than immediately. This buffering delays atmospheric collapse. Another factor is Pluto's axial tilt, which exceeds 100 degrees. This extreme obliquity produces prolonged seasons lasting decades. Regions experience continuous sunlight or darkness for extended periods, leading to uneven heating and delayed thermal equilibration. As Pluto moves away from the Sun, its southern hemisphere enters prolonged winter. However, subsurface layers retain heat accumulated during previous illumination cycles. This residual energy sustains sublimation longer than expected. Pluto's thin atmosphere also redistributes heat horizontally. Gas circulation transfers energy from warmer to cooler regions, reducing localized freezing. Even minimal atmospheric movement can influence volatile stability over large areas. Methane contributes additional complexity. Methane absorbs solar radiation more efficiently than nitrogen, warming the atmosphere and slowing nitrogen condensation. Small changes in methane concentration can disproportionately affect thermal balance. Observations indicate that methane concentration has not decreased significantly despite cooling trends. This suggests active replenishment from surface or subsurface sources rather than passive depletion. Carbon monoxide further complicates atmospheric chemistry. It acts as a cooling agent by radiating infrared energy. Variations in carbon monoxide abundance alter atmospheric temperature profiles, influencing condensation rates. These interacting components make Pluto's atmosphere highly sensitive to feedback loops. Minor changes propagate through the system, creating outcomes that diverge from linear predictions. Seasonal models struggle to capture this behavior accurately. Many rely on simplified assumptions that underestimate heat storage and volatile exchange rates. Pluto's atmosphere exposes these limitations. The delayed atmospheric response also implies that Pluto's climate operates on multi-orbit timescales. One orbit lasts 248 Earth years. Full equilibration may require several orbits, far exceeding the duration of direct observation. This raises the possibility that current conditions reflect residual effects from earlier orbital states, rather than equilibrium with present distance from the Sun. Such temporal lag challenges the notion of steady-state atmospheres on small bodies. Pluto demonstrates that equilibrium may be rarely achieved. Atmospheric escape further complicates interpretation. Ultraviolet radiation breaks apart molecules, allowing lighter atoms to escape Pluto's weak gravity. However, New Horizons measurements showed escape rates lower than anticipated. This suggests that Pluto's upper atmosphere is colder and more compact than models predicted, reducing thermal escape efficiency. Lower escape rates mean that Pluto retains its atmosphere longer, reinforcing the persistence observed from Earth. The interaction between escape and replenishment determines long-term atmospheric stability. Pluto appears to balance these processes more effectively than expected. This balance depends on subsurface reservoirs. If nitrogen ice extends below insulating layers, it can continue feeding the atmosphere long after surface conditions change. Radar and thermal modeling suggest layered ice structures that slow heat loss. These layers may preserve volatile access over extended periods. Pluto's atmosphere therefore acts as an integrated system rather than a simple response to solar distance. The mismatch between prediction and observation does not indicate error but incomplete understanding. Pluto reveals processes operating beyond simplified frameworks. The implications extend beyond Pluto. Other Kuiper Belt objects may exhibit similar delayed atmospheric behavior, challenging assumptions about volatile loss. Exoplanets in distant or eccentric orbits may also display atmospheres that persist outside expected temperature ranges. Pluto provides a natural laboratory for studying atmospheric hysteresis and long-term climate memory. These findings emphasize the importance of continuous monitoring. Single observations capture transient states rather than full cycles. Future occultation campaigns remain essential. Each data point adds resolution to Pluto's evolving atmospheric record. The persistence of Pluto's atmosphere underscores the importance of coupling surface, subsurface, and atmospheric models. No single layer operates independently. Energy transfer links all components across time. Pluto's atmospheric behavior is not anomalous when viewed through this integrated lens. Instead, it reflects the cumulative effects of slow processes interacting over long durations. Pluto does not defy physics. It exposes where simplified assumptions fail. The atmosphere remains because Pluto's system responds gradually, not instantaneously. Distance alone does not dictate collapse. Time determines outcome. Pluto's atmosphere is acting out of sequence only when sequence is defined too narrowly. When history is included, the behavior becomes consistent. This realization reframes Pluto from an exception into an expected result of complex coupling. Understanding this requires abandoning immediate cause and effect thinking. Pluto's atmosphere exists within a delayed feedback system shaped by memory and inertia. That system continues to evolve. What appears stable now may change decades later. Pluto reminds scientists that planetary atmospheres are dynamic histories, not momentary states. The dwarf planet continues to challenge assumptions not through mystery, but through persistence. Its atmosphere endures because time allows it to, and that endurance forces a re-evaluation of how planetary climates are understood. Pluto's surface is changing faster than expected. Pluto's surface is not static, frozen in time as once assumed. Instead, multiple lines of evidence indicate that its landscape is actively reshaping itself on surprisingly short timescales. Observations from the New Horizons mission, combined with long-term telescopic monitoring, reveal surface changes that challenge conventional expectations for a small, cold world at the edge of the solar system. The most striking example lies in Sputnik Planitia, the vast nitrogen ice basin dominating Pluto's encounter hemisphere. This region shows clear signs of recent resurfacing. Impact craters are nearly absent, indicating that geological activity has erased older features within the last few tens of millions of years, an extremely short period in planetary terms. Nitrogen ice behaves differently from water ice. At Pluto's surface temperatures, nitrogen is soft and mobile. It can flow like a glacier, driven by even minimal gravitational slopes. Modeling suggests that convection within thick nitrogen ice layers continuously overturns the surface, burying older terrain beneath fresher deposits. This convective motion is driven by internal heat rather than solar energy alone. Pluto retains heat from its formation and from radioactive decay in its rocky core. While modest, this heat is sufficient to drive slow but persistent movement in volatile ice layers. Methane ice also contributes to surface change. Methane condenses at slightly higher temperatures than nitrogen, forming distinct deposits along Pluto's mid-latitudes. These deposits vary in brightness and texture over time, indicating ongoing redistribution rather than permanent placement. Seasonal cycles play a major role. As Pluto's orientation relative to the Sun changes, different regions receive prolonged sunlight. This drives sublimation in some areas and deposition in others, effectively transporting material across the surface. This process is not uniform. Pluto's extreme axial tilt causes hemispheres to experience decades of continuous illumination, followed by decades of darkness. During these periods, volatile ices migrate en masse, reshaping surface patterns. Observations from Earth-based telescopes confirm changes in Pluto's brightness distribution over time. These variations correlate with predicted seasonal transport rather than observational error. One notable change involves Pluto's polar regions. During extended winter darkness, nitrogen and methane accumulate as frost. When sunlight returns, these deposits sublimate, exposing darker underlying terrain. This cyclical burial and exposure alters surface albedo over relatively short intervals. Albedo changes affect temperature. Brighter ice reflects more sunlight, remaining cooler, while darker regions absorb heat and accelerate sublimation nearby. This feedback loop amplifies regional differences and drives further redistribution. Pluto's surface therefore evolves through coupled thermal and volatile processes rather than tectonic activity in the traditional sense. Another unexpected feature is the presence of apparent dunes. Images from New Horizons revealed ridged patterns resembling wind-shaped formations. While Pluto's atmosphere is extremely thin, simulations indicate that nitrogen ice grains can be mobilized under the right conditions. Sublimation-driven winds, rather than conventional atmospheric circulation, may be responsible. As nitrogen transitions directly from solid to gas, it generates localized pressure gradients capable of moving particles. This suggests that Pluto experiences surface weathering driven by phase changes rather than wind strength. Fractures and troughs across Pluto's surface further indicate ongoing stress. These features likely result from the expansion and contraction of ice layers as temperatures fluctuate seasonally. Repeated thermal cycling causes surface materials to crack, shift, and settle, gradually altering terrain morphology. Some regions display polygonal patterns associated with convective cells beneath the surface. These patterns evolve as heat transfer continues, reshaping boundaries over time. The lack of widespread cratering across Pluto's encounter hemisphere reinforces the idea that resurfacing is widespread rather than localized. Impact rates in the Kuiper Belt are low, but not negligible. Over billions of years, even small bodies accumulate craters. Pluto's relative smoothness implies active erasure mechanisms. This erasure occurs through ice flow, deposition, and sublimation, rather than erosion by liquid water or tectonic plates. Pluto's geological activity does not require a molten interior. Instead, it relies on the unique properties of volatile ices under low gravity. This realization challenges assumptions about what constitutes geological activity. Pluto demonstrates that solid-state processes can drive planetary evolution. The presence of ammonia-rich water ice beneath the surface may further enhance activity. Ammonia lowers the freezing point of water ice, allowing subsurface layers to remain ductile. Such layers could accommodate slow deformation, influencing surface features indirectly. Thermal models suggest that Pluto may possess a subsurface ocean or partially molten layer beneath its ice shell. While unconfirmed, this possibility aligns with observed surface stresses. If present, such a layer would provide an additional heat source and mechanical decoupling between surface and interior. Even without a liquid ocean, layered ice compositions allow for differential movement that reshapes the surface. The combined effects of internal heat, volatile cycling, and seasonal extremes create a dynamic environment. Pluto's surface responds gradually but continuously to these forces. This activity contradicts earlier classifications of Pluto as geologically dead. Instead, Pluto occupies a category of slow, active worlds, where change occurs on humanly observable timescales, but without dramatic events. Comparisons with Triton, Neptune's moon, reinforce this interpretation. Triton exhibits nitrogen geysers and active resurfacing driven by similar mechanisms. Pluto and Triton likely share evolutionary pathways shaped by volatile dominance. These processes suggest that many Kuiper Belt objects may be more active than previously believed. Pluto serves as the most detailed example due to observational proximity rather than uniqueness. The changing surface also affects atmospheric behavior. Sublimating regions feed the atmosphere, while depositional zones draw gas out of it. Surface and atmosphere therefore evolve together rather than independently. Understanding Pluto's surface evolution requires treating it as a coupled climate system. Each change reflects an interaction between ice chemistry, thermal inertia, and orbital dynamics. No single factor explains the observations alone. Pluto's surface does not change because it is unstable. It changes because it is responsive. The dwarf planet reacts slowly, persistently, and predictably once all variables are considered. What once appeared static is revealed as adaptive over long durations. Pluto's surface is not eroding into chaos, it is reorganizing. And that reorganization continues quietly, reshaping expectations along with terrain. Pluto's interior may still be retaining heat. Pluto was long assumed to be a fully frozen body, geologically inert shortly after its formation. That assumption has been steadily eroded by evidence indicating that Pluto retains internal heat at levels sufficient to influence its present state. This internal energy does not manifest as volcanism or tectonics in the familiar terrestrial sense, but it plays a measurable role in shaping surface features and subsurface structure. The primary source of Pluto's internal heat is radioactive decay within its rocky core. Elements such as uranium, thorium, and potassium release energy over billions of years as they decay. Although Pluto is small, its rock fraction is substantial enough for this process to remain relevant even today. Thermal models developed after the New Horizons flyby suggest that Pluto's interior has not cooled uniformly. Instead, heat loss has been slowed by an insulating outer shell composed of layered ices. These layers limit conductive heat transfer, allowing warmer conditions to persist at depth. The presence of ammonia within Pluto's ice further complicates cooling behavior. Ammonia acts as an anti-freeze, lowering the melting point of water ice. Even small concentrations can allow subsurface layers to remain ductile or partially molten at temperatures otherwise too low for liquid water. This has led to renewed interest in the possibility of a subsurface ocean. While direct confirmation remains unavailable, several independent lines of evidence are consistent with this scenario. Chief among them is the orientation and distribution of tectonic features observed on Pluto's surface. Large-scale fractures and troughs tend to be extensional rather than compressional. This suggests that Pluto has expanded slightly over time rather than contracted. Expansion is difficult to reconcile with a purely frozen interior, but aligns with the freezing of an internal liquid layer, which would increase volume. Sputnik Planitia provides additional clues. The basin's location near Pluto's tidal axis suggests that it may sit above a mass anomaly. One explanation is a thick layer of denser material beneath the basin, potentially liquid or partially liquid, that alters Pluto's gravitational field. Gravity measurements inferred from Pluto's rotational dynamics support the presence of mass redistribution beneath the surface. While uncertainties remain, models incorporating a subsurface ocean produce better agreement with observed data than those assuming a fully solid interior. Even if a global ocean no longer exists, a partially frozen or slushy layer could persist. Such a layer would still facilitate internal heat transfer and influence surface stresses. The longevity of internal heat depends on how efficiently Pluto radiates energy into space. Its low surface temperature limits infrared emission, slowing cooling. Additionally, the low thermal conductivity of nitrogen and methane ices further impedes heat loss. This slow cooling rate explains why geological features show signs of activity far more recent than Pluto's formation. It also explains why resurfacing processes continue today. Internal heat affects not only surface deformation, but also volatile migration. Warmer subsurface regions can act as reservoirs that release gases gradually, sustaining atmospheric pressure over longer periods. This mechanism complements surface-driven sublimation, reinforcing atmospheric persistence without requiring unusually high solar input. Pluto's internal structure is therefore best understood as layered rather than uniform. A rocky core generates heat, an intermediate layer modulates transfer, and an outer shell responds dynamically to energy inputs. This structure contrasts sharply with earlier models that treated Pluto as a simple frozen sphere. Comparisons with other icy bodies reinforce this interpretation. Europa, Enceladus, and Titan all retain internal heat despite their small size relative to terrestrial planets. Pluto fits within this broader category of thermally persistent icy worlds. What distinguishes Pluto is its isolation. Without strong tidal heating from a nearby massive planet, Pluto relies almost entirely on radioactive decay and insulation. That it remains active under these conditions highlights the effectiveness of its thermal architecture. The implications extend beyond Pluto. Many Kuiper Belt objects share similar compositions and sizes. If Pluto retains heat, others may as well. This challenges the notion that distance from the Sun equates to geological inactivity. Internal heat also influences long-term stability. As heat dissipates slowly, Pluto's structure evolves predictably rather than catastrophically. There is no indication of imminent collapse or sudden change. Instead, change occurs incrementally as heat leaks outward and volatile layers respond. This slow evolution complicates attempts to define Pluto's present state. It exists within a transitional phase that may persist for hundreds of millions of years. Understanding that phase requires integrating thermal history with current observations. Pluto's interior cannot be directly sampled, but surface features act as proxies. Each fracture, basin, and resurfaced region carries information about subsurface conditions. Interpreting these signals requires caution. Multiple models can fit the same data. However, those including retained heat consistently outperform those that exclude it. The continued refinement of thermal models depends on future observations. Occultation data, rotational studies, and potential future missions will further constrain internal properties. For now, the evidence supports a Pluto that is not thermally exhausted. It is cooling, but not finished. Its interior remains an active participant in shaping surface and atmosphere. This realization reframes Pluto's role in planetary science. It is not a relic. It is a system still responding to energy stored long ago. The dwarf planet's quiet persistence demonstrates that small bodies can remain dynamic without dramatic heat sources. Internal heat does not require intensity to be influential. Duration matters more than magnitude. Pluto's interior continues to influence its evolution because it has lost heat slowly, not because it produces much. That distinction explains why activity appears subtle rather than explosive. Pluto's changes are cumulative rather than episodic. They reflect a balance between decay and insulation. This balance will eventually shift, but it has not yet. For now, Pluto remains internally warm enough to matter, and that warmth continues to shape what is seen on the surface today. Pluto's seasonal cycles operate on unfamiliar timescales. Pluto's seasons do not resemble those experienced on Earth or even on other planets in the solar system. Because of its long orbital period and extreme axial tilt, Seasonal effects unfold over centuries rather than years. This extended timing fundamentally alters how surface, atmosphere, and subsurface systems respond to solar energy. Pluto takes approximately 248 Earth years to complete a single orbit around the Sun. As a result, each season lasts several decades. During this time, entire hemispheres can remain in continuous sunlight or darkness, producing prolonged thermal extremes. Pluto's axial tilt exceeds 100 degrees, meaning it rotates effectively on its side. This orientation causes the Sun to rise and set at extreme angles, often remaining above or below the horizon for decades in certain regions. These conditions drive large-scale redistribution of volatile ices. Nitrogen, methane, and carbon monoxide migrate across the surface in response to changing illumination. Unlike Earth, where seasonal changes are shallow and repetitive, Pluto's involve wholesale relocation of surface material. When a hemisphere enters prolonged summer, solar heating causes nitrogen ice to sublimate rapidly. Gas enters the atmosphere and is transported toward cooler regions. When sunlight shifts away, the same gas condenses elsewhere, forming new deposits. This migration does not reverse cleanly with each orbit. Instead, Pluto's surface retains memory of previous seasons. Ice accumulations persist long after illumination changes, creating lagged responses. Thermal inertia plays a central role. Pluto's surface materials heat and cool slowly, preventing immediate equilibrium. As a result, peak sublimation or condensation may occur decades after the initiating change in sunlight. This delay explains why Pluto's atmosphere remained thick years after passing perihelion. The system was still responding to earlier heating rather than current distance from the Sun. Seasonal modeling indicates that Pluto's atmosphere may continue evolving well into the next century. Collapse, if it occurs, will not be abrupt. Sputnik Planitia amplifies seasonal effects. Its location and composition allow it to act as a volatile reservoir. During summer, it supplies atmospheric gas. During winter, it absorbs gas gradually. Because Sputnik Planitia sits near Pluto's tidal axis, its seasonal behavior affects global climate patterns rather than local conditions alone. Observations show that ice thickness in this region varies significantly with season. These variations influence surface elevation, stress patterns, and surrounding terrain. Seasonal loading and unloading of ice mass may contribute to tectonic features observed around the basin. Pluto's seasons also affect albedo distribution. Regions covered in fresh ice become highly reflective, reducing heating. Darker regions absorb more sunlight, accelerating local sublimation. This feedback reinforces contrast rather than smoothing it. Seasonal extremes intensify rather than average out. Methane behaves differently from nitrogen. It condenses at higher temperatures and forms stable deposits that persist through seasonal transitions. These methane-rich regions influence surface temperature by trapping heat. Methane also absorbs solar radiation more effectively in the atmosphere, contributing to thermal stratification. The interaction between methane and nitrogen cycles creates complex seasonal outcomes. One volatile may remain stable while another migrates, producing layered surface compositions. Carbon monoxide adds further complexity by acting as a radiative coolant. Its seasonal distribution affects atmospheric temperature gradients. These interacting components prevent simple predictions. Pluto's climate cannot be reduced to distance from the Sun alone. The long timescales involved also limit direct observation. Modern data covers only a small fraction of one Pluto year. Conclusions must therefore integrate modeling with partial snapshots. Historical brightness measurements help extend the record. Changes in Pluto's light curve over decades indicate evolving surface composition consistent with seasonal transport. These changes align with predicted migration paths rather than random variation. Seasonal effects extend below the surface. Heat penetrates ice layers slowly, altering subsurface temperatures long after surface illumination changes. This delayed heating influences volatile stability at depth, sustaining sublimation even when surface temperatures drop. As a result, Pluto's seasonal response is vertically layered as well as temporally delayed. This layering further decouples cause and effect. Seasonal cycles also interact with Pluto's orbital eccentricity. Its distance from the Sun varies significantly over each orbit, modifying the intensity of seasonal forcing. The combination of eccentric orbit and axial tilt produces asymmetric seasons. Some summers are warmer and longer than others. This asymmetry leaves lasting imprints on surface composition. Deposits from stronger summers may persist through weaker ones. Over multiple orbits, these imprints accumulate, shaping long-term surface evolution. This accumulation suggests that Pluto's current state reflects not one season, but many. Understanding Pluto, therefore, requires a historical perspective. Short-term measurements capture transient behavior rather than equilibrium. Pluto's seasons are not repetitive loops, but evolving sequences. Each orbit alters the starting conditions of the next. This explains why Pluto's climate appears unpredictable when viewed in isolation. Viewed over centuries, it follows consistent physical principles. The unfamiliarity lies in scale, not mechanism. Earth-based intuition struggles with processes that unfold over generations. Pluto demands patience rather than immediacy. Its seasonal cycles remind scientists that planetary climates need not operate on human timescales to be governed by known physics. Pluto does not rush toward equilibrium, it drifts toward it slowly. That drift continues now. The atmosphere, surface, and interior remain out of phase with one another, but that misalignment is expected given the timing involved. Pluto's seasons are still playing out. The present moment captures only a fraction of their progression. Future observations will reveal outcomes that current data only suggests. For now, Pluto's seasonal behavior reinforces a central theme. Time governs response, distance initiates change, but duration determines consequence. Pluto's climate is not strange because it violates expectations. It is strange because expectations were framed too narrowly. Once expanded, Pluto fits, just not quickly. Pluto's moons reveal ongoing dynamical instability. Pluto's moons provide critical evidence that the Pluto system has not settled into long-term dynamical equilibrium. The dwarf planet is orbited by 5 known satellites: Charon, Styx, Nix, Kerberos, and Hydra. While Charon dominates the system, the smaller moons display orbital characteristics that suggest continuing dynamical complexity rather than long-term stability. Charon is unusually large relative to Pluto, with a mass roughly 1/8 that of the dwarf planet. The two bodies orbit a common barycenter located outside Pluto's surface, making Pluto and Charon a true binary system rather than a primary with satellites. This configuration strongly influences the behavior of the smaller moons. Styx, Nix, Kerberos, and Hydra orbit beyond Charon in nearly circular paths, but exhibit unexpected rotational states. Rather than rotating synchronously like most moons in the solar system, these satellites tumble chaotically. Their rotation axes shift unpredictably over time. This chaotic rotation arises from competing gravitational influences. The binary nature of Pluto and Charon creates a time-varying gravitational field that prevents the smaller moons from settling into stable spin states. Each orbital pass subjects them to fluctuating torques. Observations from New Horizons confirm this behavior. Images revealed that none of the smaller moons keeps the same face oriented toward Pluto. Instead, their orientations change continually, sometimes completing full rotations in less than one orbital period. Such behavior is rare. Most moons eventually become tidally locked, rotating once per orbit. Pluto's moons demonstrate that tidal locking is not guaranteed in binary systems with strong perturbations. The moon's shapes also indicate a violent origin. They are irregular rather than spherical, suggesting formation from debris rather than direct accretion. Current models propose that the Pluto system formed after a massive collision early in its history. This collision likely produced a disk of debris from which Charon and the smaller moons formed. While Charon accreted most of the mass, the remaining material coalesced into smaller bodies. This origin explains the moon's similar compositions. Spectral analysis shows that they are dominated by water ice, unlike Pluto's nitrogen-rich surface. This distinction suggests that they formed from deeper material excavated by the collision. Despite their shared origin, the moon's current arrangement is not fully stable. Numerical simulations indicate that small perturbations could significantly alter their orbits over long timescales. Resonances between orbital periods add complexity. The moon's orbital ratios approximate integer relationships, suggesting past migration. However, they are not locked into exact resonances, indicating incomplete settling. This incomplete resonance structure implies that the system has not fully dissipated its initial energy. Residual motion continues to influence orbital evolution. Gravitational interactions among the moons further destabilize the system. Though small, their mutual influences accumulate over millions of years. Charon's tidal evolution also plays a role. Pluto and Charon are tidally locked to each other, but this state was not always present. As tidal forces slowed their rotations, energy was transferred into orbital motion. This process likely caused Charon to migrate outward from Pluto. As it did, it would have passed through resonance zones, affecting the smaller moons. Such passages can destabilize orbits, alter eccentricities, and induce chaotic motion. The current configuration may reflect the aftermath of this migration. Hydra and Nix show especially high rotational variability. Their elongated shapes make them sensitive to torque, amplifying chaotic behavior. Kerberos, despite its smaller size, exhibits similar instability. Its rotation appears erratic, even by the standards of the system. Styx, the innermost small moon, experiences the strongest perturbations due to proximity to Charon. Its orbit shows subtle variations, consistent with ongoing gravitational stress. These behaviors indicate that Pluto's moon system is dynamically young relative to the age of the solar system. While the collision that formed it occurred billions of years ago, its consequences persist. The system has not fully damped the energy introduced during formation. This persistence challenges assumptions that small satellite systems quickly stabilize. Pluto demonstrates that binary primaries can sustain long-term dynamical activity. The moons also influence Pluto indirectly. Their gravitational interactions affect Pluto's rotation and orientation slightly over time. Though these effects are small, they contribute to long-term evolution of axial orientation. This interaction links satellite dynamics with climate behavior. Changes in Pluto's orientation affect seasonal patterns, which in turn influence surface and atmospheric processes. Thus, the moons are not isolated components. They participate in system-wide coupling. The stability of the moons also constrains Pluto's internal structure. Models that include a subsurface ocean affect tidal dissipation rates, altering orbital evolution. If Pluto retains internal flexibility, energy dissipation occurs differently than in a fully rigid body. This affects how quickly the system approaches equilibrium. Current observations suggest slower dissipation, consistent with retained internal heat. This reinforces evidence from surface geology and atmospheric behavior. The moons also provide insight into the Kuiper Belt environment. Their survival indicates that Pluto's immediate surroundings are relatively free of disruptive collisions. However, their irregular shapes indicate that early impacts were significant. The absence of large craters on the moons suggests that resurfacing or fragment reaccretion may have occurred. Alternatively, small moon surfaces may be young due to gradual shedding of material during chaotic rotation. Rotational instability can cause internal stresses that fracture and redistribute surface material. Over time, this could erase older craters. This process would operate slowly but persistently. It does not require external energy input. Instead, it relies on internal stress from rotational variation. This further supports the idea that Pluto's system remains dynamically active. The moons are not static remnants. They are participants in ongoing evolution. Their behavior reflects a system still adjusting to initial conditions. The timescale of this adjustment exceeds human observation, but measurable effects remain. The Pluto system therefore provides a case study in long-term dynamical persistence. It shows that stability is not binary. Systems can remain marginally unstable without catastrophic disruption. Pluto's moons occupy that regime. They are stable enough to endure, but unstable enough to remain dynamic. This duality explains their unusual behavior. It does not require exotic physics. It requires time. The Pluto system evolves slowly, but it evolves. The moons record that evolution through their motion. Their instability is not failure, it is process. And that process continues now. Pluto's energy balance does not match its environment. One of the most persistent puzzles surrounding Pluto is how it maintains its observed thermal and energetic state despite receiving extremely limited solar energy. At its average distance of nearly 6 billion kilometers from the Sun, Pluto receives less than 1,000th of the sunlight Earth does. Under these conditions, standard models predict a far colder and more inert body than what observations indicate. Pluto's surface temperature averages around -220 degrees Celsius, yet subtle variations across its surface and atmosphere suggest active energy redistribution. These variations are inconsistent with a simple radiative equilibrium model, in which absorbed sunlight is immediately re-emitted as infrared radiation. The imbalance begins with Pluto's surface composition. Nitrogen, methane, and carbon monoxide ices dominate much of the surface, and each interacts differently with incoming radiation. Methane ice in particular absorbs solar energy efficiently in specific wavelength bands, producing localized warming. This warming does not remain confined to the surface. Heat is transferred downward into subsurface layers and laterally across regions with differing albedo. As a result, Pluto redistributes energy rather than losing it directly to space. Albedo contrasts amplify this effect. Bright nitrogen ice reflects most incoming sunlight, remaining cold, while darker methane-rich regions absorb heat. The boundary zones between these regions experience thermal gradients that drive volatile migration. This migration transports latent heat. When nitrogen sublimates, it absorbs energy. When it later condenses elsewhere, it releases that energy. This process acts as an energy conveyor, smoothing temperature extremes. Such latent heat transfer is a major component of Pluto's energy budget. It allows energy absorbed in one region to influence conditions far away, even under a thin atmosphere. Pluto's atmosphere, though tenuous, plays a disproportionate role in energy balance. Nitrogen gas transports heat through slow circulation, redistributing energy horizontally. Even small pressure gradients produce measurable effects over long durations. Methane in the atmosphere further modifies energy flow. It absorbs solar radiation at higher altitudes, warming the upper atmosphere while shading the surface below. This creates a temperature inversion that limits heat loss. New Horizons data confirmed this inversion, showing that Pluto's upper atmosphere is warmer than its lower layers. This structure contradicts earlier expectations of monotonic cooling with altitude. Carbon monoxide contributes by radiating energy away efficiently at specific infrared wavelengths. Variations in its concentration influence how rapidly Pluto cools at night and during seasonal transitions. Together, these gases create a regulated system rather than a passive one. Pluto's atmosphere adjusts its structure in response to surface conditions, altering radiative transfer. Pluto's rotation also affects energy distribution. A day on Pluto lasts over 6 Earth days, allowing prolonged heating on the sunlit side. However, the slow rotation prevents extreme temperature spikes by enabling gradual heat diffusion. Subsurface heat retention further modifies surface energy balance. Heat stored at depth during earlier seasons leaks back to the surface long after direct solar input decreases. This delayed release explains why some regions remain warmer than expected during prolonged darkness. The insulating properties of Pluto's ice layers enhance this effect. Nitrogen and methane ices conduct heat poorly, trapping energy beneath the surface. This trapped heat does not remain static. It migrates upward slowly, sustaining sublimation even when surface temperatures drop. As a result, Pluto's energy budget integrates past and present conditions. Pluto's obliquity intensifies this integration. Because hemispheres experience decades of illumination followed by decades of darkness, heat accumulation and loss occur over extended intervals. Regions emerging from long winters do not start at equilibrium. They carry thermal memory that influences subsequent evolution. This memory complicates attempts to model Pluto using instantaneous inputs. Energy balance must be treated as time-dependent rather than static. Pluto's orbital eccentricity adds another layer. Its distance from the Sun varies significantly, altering energy input over each orbit. However, the system does not respond immediately to these changes. Peak heating and peak cooling occur out of phase with orbital position. This lag is measurable in atmospheric pressure trends and surface composition changes. The mismatch between input and response initially appeared anomalous. However, when energy storage and transport mechanisms are included, the behavior aligns with physical principles. Pluto's energy balance, therefore, reflects cumulative processes rather than immediate forcing. The dwarf planet does not react instantly because it cannot dissipate energy quickly. Its environment favors retention. This retention challenges assumptions about thermal equilibrium at large heliocentric distances. Pluto demonstrates that small bodies can maintain complex energy systems without strong external input. This has implications for other Kuiper belt objects. Similar compositions and orbital characteristics suggest that Pluto is not unique. If energy balance on Pluto is regulated rather than passive, similar regulation may occur elsewhere. This affects predictions about surface activity, atmospheric persistence, and internal evolution across the outer solar system. Pluto's case shows that energy availability alone does not determine activity. Distribution and storage matter equally. Pluto's system minimizes loss and maximizes reuse. It conserves energy through phase changes and insulation. This conservation extends the lifespan of active processes. The result is a body that appears inconsistent with its environment only when environment is defined narrowly. When all energy pathways are considered, Pluto fits within known physics. The challenge lies in identifying all pathways. Pluto's energy balance is not a simple equation, it is a network. Each component influences others. Surface composition affects atmosphere. Atmosphere affects subsurface. Subsurface affects surface again. This coupling produces outcomes that defy linear expectation. Pluto does not violate thermodynamics. It exploits them. It slows energy loss. It spreads energy unevenly. It delays response. These behaviors create the appearance of excess energy. In reality, energy is conserved carefully over time. Pluto's persistence is not a mystery of generation. It is a story of retention. The dwarf planet holds on to what little it receives. That restraint sustains its activity, and that activity continues shaping Pluto today. Pluto's long-term evolution may be fundamentally misjudged. Pluto's behavior across surface, atmosphere, interior, and satellite system suggests that its long-term evolution has been underestimated. Earlier models treated Pluto as a body that reached thermal and geological equilibrium early in solar system history. Evidence accumulated since the New Horizons mission challenges that assumption across multiple independent observations. The primary issue lies in timescale. Many evolutionary models assume rapid damping of internal heat volatile loss, and orbital energy. Pluto demonstrates that these processes operate far more slowly than predicted when insulation, composition, and system architecture are fully considered. Pluto's internal heat has not dissipated completely despite its small size. Radiogenic decay persists, and layered ice shells inhibit heat loss. This combination sustains internal flexibility over billions of years, altering surface stress patterns and volatile migration. Volatile cycling further delays evolutionary closure. Nitrogen, methane, and carbon monoxide do not simply escape to space or freeze permanently. They circulate between surface, subsurface, and atmosphere over orbital timescales that exceed direct observation. This circulation introduces hysteresis into Pluto's climate. Current conditions depend as much on past states as on present inputs. Evolution therefore proceeds as a sequence of delayed responses rather than linear progression. Atmospheric escape rates reinforce this view. New Horizons measurements showed slower than expected loss, indicating that Pluto retains volatiles efficiently. Lower escape rates extend atmospheric persistence far beyond early estimates. This persistence alters surface evolution. Continued atmospheric presence enables sublimation-driven resurfacing long after models predicted atmospheric collapse. The interaction between atmosphere and surface prevents Pluto from entering a permanently frozen state. Instead, it cycles through active phases defined by orbital geometry rather than absolute distance. Pluto's extreme obliquity ensures that these phases are asymmetric. Some hemispheres accumulate volatile deposits for extended periods, while others lose them. Over multiple orbits, this produces long-term redistribution rather than depletion. The surface record reflects this redistribution. Regions with minimal cratering indicate recent renewal, while others preserve older terrain. This heterogeneity is incompatible with uniform aging. The satellite system adds further complexity. The Pluto-Charon binary creates a dynamic gravitational environment that slows energy dissipation. Smaller moons remain rotationally unstable, indicating incomplete dynamical relaxation. This instability suggests that Pluto's system has not reached a static configuration despite its age. Energy introduced during formation has not been fully dissipated. Orbital resonances among the moons remain approximate rather than exact, further indicating ongoing adjustment. Such persistence implies that Pluto's system evolves through extended metastable states rather than discrete phases. Pluto's evolution, therefore, cannot be described as finished or dormant. It remains transitional. This transition is slow but measurable. Pluto's classification as a dwarf planet does not reflect its dynamical complexity. Size alone does not determine evolutionary speed. Composition, insulation, and system structure are equally important. Pluto's large rock fraction provides heat. Its volatile rich shell provides insulation. Its binary configuration redistributes energy. Together, these factors slow change. This slow change challenges the assumption that small outer solar system bodies quickly become inert. Pluto suggests that activity scales differently with size at low temperatures. Cold environments preserve energy by limiting radiation and conduction. Thus, distance from the Sun does not guarantee dormancy. Pluto's long-term trajectory may include future atmospheric collapse, resurfacing slowdown, and interior solidification. However, these outcomes lie far beyond immediate observation. Current data captures a system still responding to conditions set hundreds of millions of years ago. That response has not completed. This has implications beyond Pluto. Models of Kuiper belt evolution often assume rapid volatile loss and surface aging. Pluto demonstrates that retention and renewal can persist. Objects once thought geologically dead may simply operate on timescales poorly suited to human observation. This reframes how activity is defined. Activity does not require dramatic expression. It can manifest as gradual redistribution, delayed equilibration, and sustained imbalance. Pluto exhibits all three. Its evolution is neither stalled nor accelerating. It is proceeding at its own pace. Understanding that pace requires abandoning assumptions derived from inner solar system bodies. Earth, Mars, and Venus evolve under strong solar forcing and higher temperatures. Pluto evolves under scarcity. Scarcity promotes conservation. Conservation extends longevity. This principle appears repeatedly across Pluto's behavior. Heat is conserved, volatiles are conserved, energy is conserved, not perfectly but effectively. This effectiveness extends Pluto's active lifespan. The system does not rush toward entropy, it resists it through structure. That resistance is passive rather than engineered. It emerges naturally from composition and configuration. Pluto therefore represents a class of worlds whose evolution is defined by restraint. They change slowly because they lose slowly. They persist because they retain. Pluto's apparent anomalies dissolve when framed within this context. It does not behave unexpectedly, it behaves patiently. That patience misleads short-term analysis, but long-term integration resolves discrepancies. Pluto's story is not one of contradiction, it is one of duration. The dwarf planet continues evolving under rules that favor memory over immediacy. Its present state reflects a balance between ancient inputs and current conditions. That balance remains unsettled, and that unsettled state is not temporary. It may persist for hundreds of millions of years. Pluto's future is not predetermined by size. It is shaped by structure, and that structure continues to moderate change. Pluto has not finished becoming what it will be. It is still becoming, slowly, persistently, within known physics, and on timescales that demand reconsideration of how planetary evolution is measured.